Well, good morning. This is day 2 of DCMIP. I hope you had a good, good night yesterday, good dinner. Was maybe heading out to downtown Boulder. Yeah, today we really dive deep into the guts. Yeah, so yesterday I guess was more like an introduction, and I was really glad to see that everybody was able to run the model. Today you will hear in the morning lectures a lot more about the making of the pudding, yeah, the recipe for building these models. We start though with a practical session. It's half an hour, and Tim and Anthony will actually tell you about our visualization options that we provided for the DCMIP workshop. So they will just do basically a live demo, and then we transition over to some of the theoretical concepts. Right.
Cool, thanks, Christiana. So we'll go over just a few different ways you can visualize the data once you get it. So firstly, go over a couple of ways that are already within Casper, which are NCView and NCVis. And then Anthony will go over some Jupyter Hub notebooks that we've made that you can run these, and then you can also edit them and plot different fields and things like that. So the first one we'll look at is NCView, which is, it needs regridded data. So that's where hopefully everyone practiced regridding back to a lat long grid for plotting on this. So if I pull up the right, which terminal is it? All right. Okay, so thank you. There's for whoever made the data that we're going to use. Okay, so simply the command for running NCView is just go NCView and then the file that you want to plot out. And this needs to be regridded. Here we've got a 1 degree dicor, so we're regridding to a 1 by 1 latitude longitude grid. So if I just simply click NCView, it'll come up with a window here. Okay. Cool. And so here we have our 3D fields that we want to plot. So here we have phi-s and ps. So this is the surface geopotential and surface pressure. So these are just at one fixed level or at the surface. And omega, t, u, v are at all the levels that you have in the domain. Z3 stands for the geopotential. And the reason we output this is actually so we can figure out where the levels are and interpolate to a fixed altitude. So this is more used for the Jupyter notebooks we'll show later. So if I click for starters here on, let's go phi-s. So here we have the vortex shedding case. So I can actually magnify, and we can see that we have this quite peaky mountain here at 20 degrees north. Right, so now say if I want to have a look at what's happening in the temperature field, I click on T, and it will now move that up. So what I often like to do is to rescale the data by right-clicking on the range. Okay, firstly, I need to move down to the bottom level. I always miss this. So by default, it goes to the model top, which of course isn't where we're interested in. So if we right-click, we can go down to 150 meters, which is the lowest midpoint level. So these are the midpoint levels, not the interface. So interface will go 0, 30, 60. So I'll go 450, and then rescale with range. And then if I want to just play a video of it, I can click that button. So something else we can do is we can look at different axes. So currently we're just looking at long lat view at a constant or at a certain height or pressure level. But we can actually do a vertical slice instead. So if we pull up this axes option, we can select which dimensions we want to look at. So here I'll choose the level on the y-axis. And I'll invert it so we have the correct lower pressure at the top. So if I plot here omega, so this is the vertical velocity, and rearrange it. Okay, So the reason it's looking like garbage at the moment is because we're at the South Pole. And because the mountain is at 20 degrees north, we actually want to skip to that. So if I move to, where's the faster way to get there? There is a skip command, but it's different on different laptops. So, yeah, that's what I'm doing. Okay, here we go. Yeah, so control and left mouse. But yeah, we can come around and help because, I mean, I wouldn't be able to remember that. So yeah, we have, I've inverted it around the wrong way. So we can see some of these vertically propagating mountain waves, gravity waves. As you see, we have a lot lower signal in this top part, and that's what the Rayleigh friction is doing, is trying to absorb some of these gravity waves. And so if you're doing test case 1, this is probably a good visualization to be able to get the braking wave.
What's the white line attempting to show?
That's an artifact of the topography, which you can remove with...
That's Antarctica, isn't it? No. You go to up, yep, and then this is actually a drug.
None. Cool, there you go. I agree, it's quite off-putting having that in there. It's, yeah, a bit wacky. Cool, are there any other features people are interested in or any questions about that?
I just remind people when you have
Yeah.
or it'll shut the whole program.
And also like, say, yeah, if say I clicked on axes and I was like, actually can't be bothered. Yeah, if I click X here, it's gonna just can't. Yeah. So I won't do that. Cool, otherwise I'll move on to NC-Vis. And of course, during the sessions in the afternoon, feel free to ask the instructors questions about these. Some of us have used NC-View more and some of us have used NC-Vis more. So yeah, we can work as a team for that.
Some of us have not used either.
So I admit I haven't really used NC-Vis much, so this will be fun. But the advantage of NC-Vis is it doesn't actually need the regridded data, so it can go on the original unstructured grid. Okay. Let's find my mouse. Right, so now we have a slightly different window. So here we have the features of interest are in either the 3D vars or the 4D vars one. So this is the surface pressure and surface geopotential and over time. And these are the three-dimensional fields and over time. So if I start with plotting the surface geopotential again, we again get a nice little mountain. And we could look at the surface pressure also. Yep, see that it's a bit lower over the mountain as expected. And then say let's do the velocity field this time. So again, it's defaulted to the model top. So we want to move the other way back down to the bottom of the model because we're looking at quite low altitudes for the features of interest. I think I go reset. No, don't. Never mind. Yeah, evidently I don't use this very much. And then I think we can just go play with the time. Yep. And we can see that nice kind of vortex jetting and tail kind of forming here. Cool, and then I think you can play around with quite a few different color bars if you go to this option here. And yeah, I think there's a lot you can play with, and some will be better than others. I'm not sure I like that one very much. Algae, let's see. Yeah, interesting. Yeah, so this gives you like a nice way to kind of play around with it. And in fact, like when we were making these test cases, these sorts of visualizations were great just to check that things were right, especially making sure that the topography was as we expected. So this is kind of like a first, just kind of play around with it. But for more kind of in-depth analysis plots, we have some Jupyter notebooks, which Anthony will now go over. So pass it over to you.
Unless you turn on there's an option on the left, quad tree fast.
Okay.
There's another option called best, which will get rid of those artifacts. But we've wasted time, like, what are these artifacts, what's going on with the model? There's a plot, NCViz.
Okay, what is that option that you were talking about?
KD tree.
KD tree. It's only for unstructured data. If you're plotting lat long, it doesn't matter. But
Okay.
it's the unstructured rendering option.
Okay, cool. Appreciate that.
Okay, so we've prepared a few Jupyter notebooks. In normal times, they would be very easy to use. Okay, anyways. So we have instructions in the editors and visualization page about how to use these. They're all in this GitHub repo. So a lot of you have used some other scripts here, but here in this plotting, we have a number of Jupyter notebooks. So we have one for the gap flow, we have one for the gravity wave, we have one for the squall line, and we have one for the vortex shedding. And then we also have an example to create a video, and we have an example using CartoPy. So feel free to play around with these. So normally, launching Jupyter Hub would be very easy. You just go to Jupyter Hub, and then you start, and then so you need to do this, and then go back, and then you change the project account, and you change this to workshop, and then you would click Launch Server. Unfortunately, this is not working at the moment, so there's a slightly more involved workaround. So we have these instructions linked here. So the way this goes is, so you do Q interactive at Casper, and then you need the account number. So, and then now you wait. So the job is now in queue. This may take a while, depending on how many people are trying to do this at the same time. Yes?
Do you do the pass in the workshop queue option? That was faster yesterday.
Okay. Well, how do you do that?
You do a dash Q workshop.
Okay. Dash Q workshop. No, that's just the GPU reservation. Request rejected wall clock. Yeah. Okay. Wall time equals 2 hours. Okay. So you can just do this command. You'll launch a interactive job eventually. So while we're waiting for that, so you'll notice that, so if we just like open one of these up, let's say the squall line. So, okay, import statements. There's a lot of things to set. So you pick which model you're using. Is it the resolution? Are you in hydrostatic or non-hydrostatic mode? And then you will need to set all the paths to your own run output. All of this is set up for latitude, longitude output. So if you're in FV3 or MPAS, you need to regrid your data before doing this. Later in the week, if people are interested in directly visualizing the unstructured data in these notebooks, there is an option to use UX array. It is a bit finicky, so the standard plots are reliable. Yeah. Open the data sets, and then you can pick which variables to visualize. So some of this is model dependent, and also which test case you're using. So for the squall line, we're using Kessler physics. So we have a number of these 2D fields. So prec-T is the total column precipitation. TMQ is the total column moisture. And then TM rain, so this is total column rain, and then total column cloud liquid. And then we have a number of these 3D fields. So T, temperature, U, V, velocities. W is the vertical velocity. This is a bit finicky for the various options. And then we have the horizontal divergence, horizontal vorticity. This is just the specific humidity. And then for the squall line, we also have this radar reflectivity option. Has this started? This has started. Okay, so back to this. Okay, so now we're in this interactive job. You'll see that we're not on a login node anymore. So what you do is you'll need to load the NCAR env in module and the conda module. And then you'll need to conda activate NPL. And then, okay, so now you see we have NPL, and then you start Jupyter. So you get this warning that this has been deprecated in favor of Jupyter Hub. Okay, and then now we have this. So now what you do is you copy this command into another terminal window, and then you'll need to say yes, and you'll need to, so this will take there's a bit of a delay, but you do need to log in again. So enter your password, and then you do two-factor authentication. And then after you've done two-factor authentication, this doesn't respond. So then what you go back here, and then you get this link, and then you just copy this into your browser.
Is there instructions for all this yet?
Yes.
Okay.
So the instructions are linked here.
Okay, great.
So if you click, yeah, this has all the instructions. But so, yes. The font a bit larger. Okay. What was my password for this? No, or so the first time you use a token, but then you make a password. So I made the password. Let me find it. Okay. Log in. Not now. Okay. So, okay. It works. So here we have the, okay, so now, okay, we can actually look at the squall line. Run all of these. So this is with some output that I grabbed from one of the MPAS groups. So here you'll notice that we have some finicky things. Well, okay, so first here of all, if we have 3D data, then we need to do interpolation. So here we have, if you're looking at the vorticity or the divergence, you need to interpolate the u and v and then interpolate. If you're looking at the vertical velocity, this is a bit finicky. MPass will output the vertical velocity, so that's very nice, it works. SE and FV3 do not output a vertical velocity, so there are separate interpolation routines, yes.
Why are we interpolating? Are they on different times?
So SE and FV3 output data on pressure levels, and we will be visualizing everything on height levels. So we have, yeah.
And also, yeah, just so you can choose which altitude you want to look at. Because you might want to look at something which is between levels.
Yeah. So these interpolation routines handle the pressure level to height coordinate change as well. And then for 2D fields, no interpolation needed. For vorticity and divergence, we need to compute those. For precipitation, we convert the units to millimeters per day. Yeah. For the squall line, we define a special radar reflectivity color map here. And then, wait, did I run these? Yeah. And then you get this plot. So this is 45 minutes, 90 minutes, 135, 180. We have the color bar on the right. And then, so you can, obviously, there's lots to modify. So you can pick which height level, which variables. You can modify the figure aesthetics, the layout. And then also, for MPass, we know that the model is not symmetric about the equator. And for many of the test cases, we do have symmetric initial conditions. So we can also measure how much asymmetry the model is creating. So a bit. Any questions? I will caveat that for the mounting gravity wave, if you're looking at the vertical velocity for the mounting gravity wave, that interpolation routine has not been written yet. So one of you will need to write it. And then, yeah, so feel free to create a fork of this repo. Just go crazy with whatever you want to. Questions? Yes?
So when we get these notebooks, do we need to clone them before we make errors?
Well, so in principle, you do. So yes, you do need to clone them to Casper. Well, so they're already in the DCMIP-2025 repo. So if you've cloned that, they're already there. If you're making changes and you want to collaborate with others on the changes, then you should create a fork. But if you're just making local changes and you aren't going to push anything, then you don't need to fork anything. Yes?
Very naive question because I'm not very good at this. How do you make, I cloned into my work directory.
Yes.
This thing is putting me into my home directory. How do I get to my work directory?
From?
Right now, I think I'm in my home directory in Jupyter Hub.
Oh,
Like everything on the left side is all the files in my home directory.
right. I don't know.
File input tab.
You might consider creating a symbolic link.
Yeah.
Okay.
But
Using our method where we're not
Mm,
where you launch the notebook from. Where you launch the notebook from is where, yeah,
okay.
you can do that.
Yes.
Just out of curiosity, it looks like from the code you're computing vorticity and divergence from the wind fields
Yes.
as opposed to having the model output divergence.
I don't think the model's output. No. Yeah. Yes. So for these test cases, it's you can just like not really. So you can just like look at the output for all the time steps. Yeah. Okay. No more questions. We'll be around in the afternoon for more questions if people have them. Yeah. Very nice. Okay. So next talk.
Can I ask a quick question about
Panoply.
Panoply? Well,
Panoply.
Panoply is
How-
how, you know, we pronounce that term in history.
Okay.
Because it's a shield system.
Uh-huh.
Anyway, I tried. My computer, I've used it for years. I tried downloading the regridded net CDF files, and it won't view them. Has anybody seen that yet? It says it's basically in the format it doesn't recognize, which surprised me. I expected that for the ungridded, but when I regridded it, it still didn't work. So I was just curious if anybody's tried that.
You weren't working with MPass output, right?
No, it was FV3.
If you regrid it, it might be
I
a
regridded it.
net
that's what I was-
CDF4. The regridder puts it in net CDF4. And if it's an older app, it can only read net CDF3.
Okay, well, I just installed it recently, so it's whatever, I guess, the latest version, maybe that's the problem. It doesn't read net CDF4s, although that surprises me considering how quickly they update it.
That's just a guess, not a...
That's a good question. Yeah, it was available at some point, but I think currently the Casper maybe was available even on the ratio at some point. But good question. We could maybe look into it. Panoply is a really nice tool. If you haven't used it, it's available for download. It's a NASA tool, a visualization tool. It's like a GUI, but way more sophisticated than NCView and NCVis actually.
And then I guess MCL is sort of an option. It's black magic.
Yeah, we actually worked, I guess, Tim and others yesterday worked on an NCL. NCL is NCAR Command Language. For those who haven't seen this, now I guess everybody uses Python, but it's still available and it's still powerful. And we have yesterday played around with a kinetic energy spectrum. So Adam showed you, for example, effective resolution plots, remember? Or we can bring them back here also, actually in my lecture on diffusion. And there is a nice NCR script which we can offer, yeah, if you have a need or a desire to plot kinetic energy spectra, to see diffusion properties, for example.
I might have a solution for the Panoply thing. When it's regridded, it has .regrid .nc4. My guess is Panoply's reading the dot after looking for a netcdf file. So if you modify the file name to like an underscore and try it, you'll probably get it to work.
Thanks.
Yeah, it could be. Okay, thanks so much. Give them a hand here. I will start the technical session this morning, and we are just switching computers here for a minute. I will talk about really the guts of the modeling decisions, and I will show you how many there are. I guess maybe it's even a subset. And the guts, I mean, you need to decide which equation to solve. Yeah, that's a very basic decision to make, and it's not clear which one. So it depends actually on your needs and application. And then I will show you a couple of other decisions, for example, the computational mesh. Yeah, so that's the next decision. After this talk, we will then Owen will dive into the numerical discretizations. So after we make those two decisions, just the equation set and the computational grid, we then can work on solving the equations on a computational mesh. And he's mostly talking about the horizontal mesh. Tomorrow we have Dave Randall here from Colorado State University, and he will also talk about the spatial discretization in the vertical. Yeah, so we have these two dimensions. They are actually treated very differently and typically. And on top, we have, Pete Bosler here tomorrow, who talks about temporal, so discretizations in time. So it will be a really, deep dive into those concepts, although we are not claiming we make you experts here during this week, but you at least have seen the concepts. Yeah, that's at least what we can do, and you can follow up later. All right. Yeah, so this is really the first, well, I guess you have seen a lot of equations in your studies or as postdocs or even as career scientists. So here I want to just give you a structured walkthrough. What are the decisions to worry about when you build dynamical cores? I actually want to start with more generic remarks, and Adam, he mentioned that briefly, but of course, in the end, let's not forget that when we think about climate model in particular, weather models also, but climate models in particular have many more components than just the atmospheric component. Yeah, so the atmospheric component is really just, you see it here, just a really tiny piece, an important piece, of course, but a tiny piece of the whole picture. For climate models, you also, of course, want to worry about oceans or ice in general. Lakes are in that category as well. Solid earth physics, volcanic eruptions, not necessarily coupled, interactively coupled and modeled, but at least you need input from volcanic eruptions, or you need, and this is true for both weather and climate models, you need land data, not just data. Land data means, of course, you need topography, you need land use, maybe need to know what soil type you have. Those different soils have different characteristics in terms of their soil moisture, for example. But also, some models have inactive vegetation, yeah, so they can grow crops. Irrigation maybe is part of a land model. So there are many, many aspects actually in the land model. Soil moisture is an important one, of course, for evaporation. Some models, have scenarios in them where when we look at these big intercomparison projects like CMIP, that's actually an effort where we kind of integrate people, like not explicitly, but we have scenarios, for example, emission scenarios, carbon dioxide emission scenarios, methane, or even pollutants, or sulfur, sulfate, other species. And yes, you may want to worry about space impacts, like fluctuations of the solar radiation, which of course happens over long timescales. Yeah. So, but yeah, for really long timescales, paleoclimate, this would be a decisive thing to have. Yeah. Okay. Today we are not really focusing on any of these, but the atmosphere. So we are diving into this component, and here is really a schematic view. I bet you have seen this many times. So just really briefly, let me kind of remind you what we are looking at here. So we here actually see a latitude-longitude mesh here now projected onto the sphere. And imagine that we are now here solving equations of motion, and you will see them in a minute, variables basically, and partial differential equations at any of these little grid boxes. Yeah, so you see the grid boxes here, and note there's also a vertical dimension. Yeah, so we have a 3D system, and technically it's 4D when you think about time. Yeah, we step forward in time in these models. And everything we do on this model grid, we call the dynamical core. Oopsie, that was too quick. And there will be many, we are deciding even at this point on the resolution, the grid spacing like 100 kilometers. Yeah, that's a very typical resolution for climate models. And we note that there are many, many things in the atmosphere that are way smaller than 100 kilometers. Yeah, and those things we cannot model explicitly. And they are here in that box, which, oh man, I finger is too quick. There in the box we call physical parameterizations. Yeah, so everything we cannot model at the scale we are choosing, 100 kilometers, for example, needs to be mimicked by physics. Like even in the spotlight test case, we have a so-called Kessler physics scheme activated, which is mimicking precipitation, cloud action. So yeah, not evaporation, but condensation and rain formation. And those things, you kind of see a couple of the processes here. You know, rain or snow is part of it, but also there are these exchanges here, you know, near the model bottom with the surface, momentum, heat, water, and so on. And this is even, you know, different exchange over oceans versus over land. So solar radiation is another example, turbulence, mixing in the lower boundary layer. These are typical physical parameterizations that are way smaller than 100 kilometers in my case. Yeah? And they do need to be there. We have typically a really hard time in GCMs to do this right. Yeah? We do basically, it's an estimation technique. We are just, you know, approximating, and there will be a lecture on Friday, yeah, on physics, how this is done here in the NCAR model, for example. But we are basically estimating the effects of small scales on the resolved scale, and the resolved scale is, yeah, 100 kilometer scale, although, you know, Adam already told you, the grid spacing isn't the resolved scale technically. Yeah? We need a couple of grid points to resolve a feature, like at least 3 or 4, typically a wave. You cannot, for example, resolve a wave with 1 grid point. Okay, so we are now diving just into the DICOR, so just into the computational mesh, and typically this is, we call the dynamical core. And here you see it a little bit in a different schematic view. I'm not certain you can read it. So these are basically, the DICOR is capturing the adiabatic processes, yeah, without the rain, without the physics interaction. Physics will be in this other big box, yeah, the subgrid scale processes we are not capturing explicitly. All right, and if you, I don't know whether it's too small to read, but basically I'm already pointing out that there are a couple of variables to worry about, yeah, pressure, wind, you know, temperature, and they're all correlated, and that's now captured in the equation of motion, yeah, in our partial differential equation. There's also something that we will look at on Thursday, I believe, or do it, or maybe I do it tomorrow, no, tomorrow even. There is a need for diffusion, and we actually already pointed out to you that we have lots of diffusion knobs in these models, and this is something you should definitely try. Yeah? Maybe turn on and off, or strengthen or lessen the strength of the diffusion, and you will see the impacts of the diffusion here on the flow fields, even in those idealized test cases. Okay, so let's think about choices to make, yeah, before we see the equations. I'm actually in this presentation, I'm really only focusing on these two. Yeah, so I will show you the equation sets, potential choices you can make about the prognostic variables. And these are two different things. Yeah, you will see in a minute. And then we worry about the computational mesh. And in addition, that's an important decision. But the next decision, which is non-trivial, is then you have a mesh, like a cube sphere mesh, but where do you put your variables? Do you put them right in the middle? Do you put them at the edges, corners? Where do you put them? And that's called grid staggering. And we worry about this today in the horizontal direction. This is also a topic for Dave Randall tomorrow when he talks about the vertical discretization, because grid staggering comes in also. Okay, and in addition to those two, we need to worry just in general. We need to worry about the numerical method. That's Owen and others talk about that, both in spatial and in the temporal domain. We worry whether our model conserves things like dry air mass, for example, or energy, things we would like, yeah, as physicists. We would like conservation of things we know should be conserved. That's not necessarily a given, yeah, and it depends on choices we already made up in our equation set, for example. The next thing to worry about is, the vertical coordinate, which is really an independent decision from the horizontal coordinate. And that comes in also with the question where to put things. For example, would you put the vertical velocity at the same location as temperature or not? Very detailed decisions here to make. And again, every decision, there's no free lunch. Yeah, every decision you make has a consequence, but good and bad often. Yeah, so it's never really perfect. So in the end, it's almost like when I don't know, you probably have been to classical concerts. There are lots of musicians. They all play their instrument. but in order to enjoy the concert experience, they need to play well together. And that's exactly what die cores do. Yeah, all the decisions we make need to play well with each other. Yeah, and it's not a single decision that makes a die core great. Yeah, but it's the composition of the many decisions. Right. We need to worry about diffusion and filtering, otherwise your model will blow up on you. Yeah, and it might even this week, yeah, if you are overdoing your diffusion setting or underdoing it. And then we need to worry about tuning. And for example, tuning diffusion coefficient is one way of tuning, but also tuning comes in later in physics, yeah, tuning empirical factors in the physics. Well, we need to, at some point, need to worry how we even include the moisture. That's another independent decision. So far, we talked about the dry dynamical core, but at some point, we have the moisture, like the score line. And even which moisture? Is it just vapor? Is it liquid? Is it rain liquid and cloud liquid? You know, and is this ice? You know, so you maybe have even 10 different forms of moisture to worry about. Whirlpool is another one. And then you want to, in the end, couple the die core to the physics package. And that's a non-trivial task as well. And again, you could play with that in a scoreline test case because it turns out that die cores in physics run with different time steps. Yeah? So typically a die core needs a finer or a shorter time step, otherwise it blows up on you. So often we are doing a couple of die core steps and then we do a physics step and we do a big dump of physics tendency into the die core, or maybe not. Yeah, so this is actually a decision to make. Do you dump physics tendencies into the die core right away, or do you dribble it in? So these are decisions we touch upon a little later this week. Okay. The other thing we should worry about, and again, I'm only pointing here to one aspect in my presentation, but of course, if you design a die core, you want everything, yeah? You want an accurate model, you want a stable model, you want actually a simple model. You want to be a computational efficient model that runs really fast. It should be a parallel model, of course, and it should obey these physical constraints. Conservation properties, for example, then you need to ask which ones, yeah? There are many, potentially. And you can never conserve everything you want. Yeah, you have a couple of choices to make. The easiest one is probably a mass conservation. Energy conservation gets tricky already because we have diffusion, and diffusion takes away kinetic energy. And now you need to decide what to do with, kinetic energy friction, whether it's going back into heat. Yeah, you can play those games. Yeah, or you need to worry about also how you treat tracers, whether you allow them, which would be a bad choice, to get negative tracers, negative moisture doesn't exist. Yeah, models typically blow up on you if you allow your numerical scheme to do that. Yeah, so you need to worry about something called positive definite or monotonic. If you do, that brings in potentially diffusion, which you don't want. So again, there is no free lunch. Yeah, so we need to worry about all those aspects. And last but not least, I want a good, truthful representation of unresolved processes. I guess in our die core, it's mostly the dissipation that we're worried about. The subgrid scale is also, of course, in the physics, represented in the physics. All right, so let's dive into the guts. We have 6 conservation laws to worry about in the die core, 3 equations of motion, or I guess this is called the equations of motion, 3 equations for the momentum conservation. This is for u, v, w, the 3 velocities. We have one, this is the conservation of mass, which is also the continuity equation, same thing. We have the conservation of energy equation, or the thermodynamic equation to worry about, and then an equation of state, or you call it ideal gas law. Yeah? Those are the 6 equations, and they come with 6 unknowns. These unknowns are not clear yet. Yeah? They can be different unknowns, but there are 6. Yeah? You need 6 equations, 6 unknowns to close the system, otherwise you can't do anything. Yeah? It's highly nonlinear, it's highly coupled, there are very few analytic solutions. Here in DCMIP, we dream up sometimes steady state solutions. So sometimes, yes, simple, if you really give it really simple initial condition, they are steady state. That's actually something to test sometimes. Yeah? The baroclinic wave test case that we also have can do that. Typically, maybe I should also add, we haven't added moisture, we haven't added any tracers yet. So if you now have moisture, we need extra equations. These are tracer advection equations for vapor, cloud liquid water, cloud rainwater, or whatever. So each new variable that you bring in has a new equation. And now you make your choices, or that also applies to pollutants, like, some sulfate, or whatever, volcanic eruptions, for example, emit those, yeah, or chemistry components. All right. Here you see a couple of the choices that you might want. Temperature, pressure, these are choices for the unknowns, the variables, the wind velocity, and these are typical names, yeah, UV, see? UVW and density, specific humidity. Not every variable will be present in every die core because it depends on the design, yeah. Okay, so let's kind of dive into the design decisions for the equation set. So this is actually now from a publication by a UK Met Office group, Andy White and colleagues. And they published this in, 20 years ago. So you see up there the reference. They published actually this matrix of the decision tree. And this is really just a snapshot. There are many more equation sets you maybe can use, not necessarily for climate and weather, but for studies at your university, for idealized studies. You know, there are shallow water equations, there's a quasi-geostrophic equation set, there are unelastic equations, there are many more. Yeah, I'm not talking about the ones that aren't typically present in weather and climate models, but there are many more. All right. So here you see the matrix. So we really would like what we call the original equations, and we never do that because we cannot, and I will show you in a minute why not. And we are typically in this arena of these decisions, non-hydrostatic deep, quasi-hydrostatic, or this is non-hydrostatic shallow, and this is hydrostatic shallow or called primitive equation model. And I will walk you through this, what it means actually, these acronyms. The main decision is deep versus shallow. This is a decision, and hydrostatic versus non-hydrostatic. Okay. Before I do that, I want to note that there are two approximations in any model. Therefore, we never use original equations, the Euler equations, but we just don't know how to do that. Yeah? One approximation that's currently in all models that I know of, at least operational models, is that we assume that the Earth is a perfect sphere. It's not. Yeah. So here is, of course, I'm exaggerating a little bit, but the Earth is actually a little wider at the equator, about 20 kilometers, the radius, and it should be an oval shape, yeah, or ellipse. And nobody does that, although there are some interesting research papers about that, especially from the UK Met Office and other groups in Europe that maybe want to pursue that, actually. Yeah, but currently, no operational model does an oval shape Earth. Yeah. So that's number one that's currently preventing us from going after the original equation. And number two is that the original equation would actually need the actual gravity. And actual gravity is really complicated. Yeah? So models typically use constant gravity, or sometimes you let the gravity vary in the vertical direction. But that's it. Yeah? That's not how gravity actually looks in nature. So this is actually based on measurements. These are measurements of gravity anomalies in some milligauss unit. Let's not worry about it. But gravity is not a constant. It depends actually on the structure of the Earth. There's this crust. And here you see that's actually highly variable. Yeah? So nobody does that. Yeah? So we are typically assuming G constant or G, well, constant, but with variations in the vertical. All right. Okay. So here is the best you can do. This is kind of the next step up from the original equation. This is almost not approximated. This only has this spherical approximation and the gravity approximation, but the gravity is allowed. Here you see the G is allowed actually to G is a gravitational constant, NA is the radius of the Earth, the constant, and R is actually the distance from the midpoint of the Earth to any point. So here we do have that dependence of gravity at dependence on the location in the vertical direction. So this is, you kind of see, and I'm presenting this in spherical coordinates, which, again, I will make a claim later, nobody will do that. Yeah? So there's so many more decisions that Mark Taylor will probably show you his equation set, and you will not see this. Yeah. So we will make decisions also on the types of meshes, cube sphere meshes, typically have a different notation, and spherical coordinates are maybe not the typical pick. Yeah. Okay, so we see these are now the momentum equations. You see the total derivatives, you see metric terms. This is in spherical coordinates, metric terms popping up, pressure gradient forces, G, gravity. Here we have Coriolis forces, and we have diffusion. Here second order Laplacian diffusion. This is a continuity equation here written with the density, oopsie, and I have the thermodynamic equation, and that's only one choice of the thermodynamic equation. There are many more, and I have the ideal gas law down here. Yeah, but this is the best you can do. And there are models that do that. I list a couple, ICON, the German Weather Service model, and Max Planck Institute, AMPAS can do that. Endgame is the UK Met Office model, and now we have a development version of the spectral element model that also can do the deep atmosphere non-hydrostatic equation set. That's not standard yet, but it will be available in the future in NCAR. Okay, that's the best you can do, but no, it's rare. Yeah, so just a few models. And the next thing, and this is very rare, people normally don't do that, but it could be done. This is actually now, and you see in the hierarchy where this sits, it's still in the deep atmosphere hierarchy, but here we are now crossing out the vertical acceleration. We make it a hydrostatic, and we call it quasi-hydrostatic because it's not really just hydrostatic. But we cross out the vertical acceleration here in the vertical advection, vertical momentum equation, and we also cross out the diffusion. And that makes it so-called quasi-hydrostatic deep atmosphere. There's no model I'm aware of that does this currently. Yeah? So typically model would already go to a non-hydrostatic design, but this could be done. Maybe NCAR is attempting that though. I don't quite know. Owen told me, I think, that NCAR may be interested in this. What we typically have, and this is typically, MPAS is probably a little more advanced, but the typical, like the UFS from the National Weather Service, the Unified Forecast System, and other models, they do typically that. And now we are in that hierarchy here, down here, in so-called, in the shallow atmosphere branch of modeling. Non-hydrostatic. And what does that mean? Shallow atmosphere is a big decision, but a very convenient decision. A lot of people make that decision. It's actually justified if you have low model tops, 40 kilometers or so. Although recent literature has debated whether we should bring back, and you see a really big decision here, we are crossing out some of the Coriolis forces with this, in this equation set. And you wonder why, because it's a must. It's not my choice, it's actually must, because if we don't, we are violating angular momentum conservation with such an equation set. So it's a necessity, if you go to shallow atmosphere, to also cross out Coriolis forces. They are believed to be the ones that are less important, but it's not 100% clear whether we will be holding that statement in the future. But let's maybe guide you through it. There's, what is the, basically you see here what the decision is. So you see that we are crossing out some metric terms whenever we see R from, this is just a distance from a center to any point in the vertical, we are replacing that with a constant radius. Yeah, so that's a decision here now in this shallow atmosphere approximation. You see that over here and here, and then the dr just becomes a ddz, which is just the derivative with respect to height above ground, yeah, the ddz derivative. And we now need to keep g constant. We are no longer allowed, in order to conserve angular momentum, we are no longer allowed to vary g in the vertical. So this is now a constant 9.81 or whatever you pick. Yeah? So this is now big, and let me clean this up. So I think here it is. So this is still the same equation now cleaned up. Yeah? So I now drop basically the things I just crossed out. And I have now one more box to cover, and that is what you probably find in all climate models. So this is, as I note here, this is actually very convenient. This non-hydrostatic shallow atmosphere equation set, very convenient for weather models. For climate models, we typically go, and let's go here, we go one more step, and that would be the hydrostatic approximation. And it's really a small step from the non-hydrostatic to the, from non-hydrostatic shallow to hydrostatic shallow. We are just crossing out the acceleration in the vertical, and that makes our model now a hydrostatic shallow atmosphere model, or we call it primitive equation model. Primitive equation, that's a keyword, like a jargon for that category. And this is a very common approach, and basically I claim, all climate models run like 100-kilometer resolution, are probably that. Yeah, Joshua.
Can I ask a question on
assume it to be 0, are we assuming the density is just of the main fluid and not the tracers?
This is for dry. I know where you're heading. We are assuming this is a density of dry air mass. Yeah, we are not having any moisture in here. That's not correct if we have moisture here. If this is a moist density, we have sources and sinks of moisture in the continuity equation.
And it's true for chemistry as well.
Yes.
Production and loss.
Yeah. Yes. Yes. Yeah. So we have in the continuity equation we have no production and loss terms. That should be okay for dry air mass. Once you have a moist mix, that's not okay. Yeah. So there are these details, and I'm not even including any moisture aspects here. Right. Yeah. So when you think about our modeling portfolio, we have in FE3 we have the shallow atmosphere non-hydrostatic equation set. That's we actually, maybe I should point out, we have in some configurations, we even go after a hydrostatic approximation. That's true actually for FE3 and SE for test case 1 and 2. We run them actually as hydrostatic models. So this would actually be the equation set for the hydrostatic model. This MPAS is, we are not running in the deep atmosphere. Let's see, we have the deep atmosphere. We are not running MPAS. Technically, MPAS has this capability, but not here in DCMIP. So MPAS is actually an interesting one, which technically is an inconsistent one. I'm not even capturing MPAS here. MPAS is non-hydrostatic, but they have a shallow atmosphere. Yeah, it's very complicated actually. So MPAS has a shallow atmosphere approximation technique. They do that, but by design, I don't think they forgot, they don't cross out the Coriolis forces. So technically it's angular momentum non-conserving by design. So I don't know exactly what that means for the model. I don't think we know yet, but technically it's an inconsistent data equation set for MPAS. All right. Okay, any questions here? Yeah, Amber.
As far as I know, hydrostatic models are often significantly more efficient, or like a factor 5 or something,
Yeah.
non-hydrostatic.
No, factor 5, I don't think so. It's
Okay.
it can be. I don't know. Mark, is that factor 2?
Maybe more factor 2. Yeah.
Well, it also
Depends.
depends on how many tracers you have, which hide the cost. But I think in the
But just the switch between hydrostatic
factor 2 in the dynamics.
dynamics, right? In the dynamics only, the physics would be unaffected by that. Mhm.
Is that that seems surprising considering it's just one term?
Yes, it's due to the presence of sound waves. That's a nuisance. So if you have non-hydrostatic configurations, you allow sound waves, and they are a nuisance. They travel 330 meters per second, and now you worry about numerics and time step and everything, and that makes it expensive. Yeah.
Are the majority of these that are used in climate and weather, are they explicit? Because that gets back to, if you use implicit, then you can go with a larger time.
Yeah, that's true. They do implicit in the vertical, but it's still more to do. There's also typically one more equation to solve. Depends a little on the design, I should say. Often there's one more equation to solve, yeah, and then Tom, yeah.
I may be just misunderstanding, but are these technically the Euler equations? Because they do have a viscosity term in the momentum equations.
I guess the Euler equations they do have the Laplace. No, the Euler equations are unapproximated original. This is what I called original. They don't have the approximation of spherical Earth. They have no approximation of gravity constant. So that would be the Euler equation. Yeah, you are close to the Euler equations. Let's say it this way. Yes. Tom, I think. Yeah.
I was just going to add about the hydrostatic.
Yes.
I guess my question is always, it's the choices that you then have to make about your discretization in response to that term being crossed out that makes it much more expensive being hydrostatic.
Yeah.
So Endgame has a hydrostatic switch where you can turn this off, but it doesn't make it cheaper at all to turn it off because it still goes through the whole same numerical discretization.
In some models, the cost is only 20-30% more, actually. It's not guaranteed, it depends actually on the designs.
We'll see a little more tomorrow.
Yeah, oh, perfect, yeah.
I was going to say a quick comment with the hydrostatic primitive equation set here. There is a GCM that's out there. It's been out for 30 years using the planetary community called EPIC, Explicit Planetary Isentropic Coordinate. it actually keeps the oblateness factor in there, because with the outer planets, you can visually see the oblateness.
Yes, good
So there
point.
is a way of dealing with
There
it.
is a way to do it, yes, I agree. There is a way to do that, and we might see it in the future. Maybe that's our next big frontier, actually, for the dipole world, actually, to get rid of that approximation. Whether it matters or not, good question. It's 20 kilometers, yes, it's sizable, but is it enough to be seen? We don't know. Yeah.
If you want to adapt to a giant planet, you can't get past
That
it.
is true.
Your mic died.
Edge. So maybe I can, let's see. Should I do, oh, all right, I don't know where that happened. Okay, thank you. All right. Okay, I will jump into the computational grids here in a minute, but let's maybe do a few more, think about a few more decisions. We are not done yet, yeah? So once you decide whether it's hydrostatic, non-hydrostatic, deep or shallow, you also worry about the choice of your coordinate system. I showed you the equations here in spherical coordinates, which also expose so-called metric terms in that spherical domain. But you could also do it in Cartesian meshes, or you have mapped coordinates. A cubed sphere is technically a mapped coordinate. And then the equations do look different, yeah? And that's why I claim actually none of our models will look like what I just showed you, yeah, explicitly when you look at the actual publications. We also need to make a decision on Lagrangian versus Eulerian form. And I'll show you in a minute what I mean by that. We need to make a decision on the so-called advective form versus flux form. This is a way of writing the equations. And that also brings in a decision on the choice of variables in the equation of motion. I showed you just really plain variables like temperature, U, V, W. But actually, it's not the only choice. Here, I point out two more choices. Temperature is not a must, and many, many models don't use temperature, but use potential temperature as their thermodynamic variable. Yeah, so that's a consequence. It's a design decision that has consequences elsewhere later. And another one you could do, instead of U and V in your two wind speeds, you could also do like a prognostic equation of divergence and vorticity, relative vorticity. Yeah, so this is another one that you can interchange. And one of the I guess the Eulerian dichromate that now is no longer available here at NCAR was based on vorticity and divergence, not on U and V, actually. And then we will learn a lot about the vertical coordinates from Dave Randall tomorrow. Okay. Here is an example of Lagrangian versus Eulerian framework. Lagrangian means that you would keep the total time derivative. Here's an example of the continuity equation and how it would look. And that's different than the so-called Eulerian form, where we expose the partial derivatives. So now we blow up the total time derivative to the partials. And this now becomes, this is even nice. This is actually a flux form. This is now the continuity equation in flux form. And that has many advantages, actually, in numerical schemes, as we might hear from Owen today. So this is actually enabling you to do really easy mass conservation. Okay, another one is the so-called advective form versus flux form. I'm already alluded to flux form, but that's also important for tracers. So imagine this is a tracer advection equation. Q would be moisture or any tracer you want. And this would be now the tracer advection equation here in so-called advective form, or here if you blow up the total time derivative, here you see it. That is less well suited for mass conservation, for tracer mass conservation. You often want to go to the so-called flux form, and now you see the flux form here for the tracer equation, which brings in the density, the rho of the air, dry air, for example, and that multiplies. So this is basically a mix of the continuity equation and the tracer advection equation together. And again, the second form is way better for mass conservation. Yeah, so these are decisions to make. Okay. Okay. I want to spend the last 20 minutes or so on grids, and this is really fun, and really, yeah, you probably have seen a few, but I guess the drive towards non-uniform grids, or I shouldn't say non-uniform, actually more uniform. Non-uniform grids would capture grids that are really very different in grid size. the Laplon grid, or traditional Laplon grid, is actually highly non-uniform. Yeah? When you consider the convergence of the meridians in the polar region, we are converging there. It's really tight grid spacing there. So there was a desire about 20 years ago to go away from that constraint of the latitude-longitude grids, which are really a nuisance at the pole points. And we then had many suggestions in the literature to go towards highly uniform coverage in terms of grid spacings. You need to make a decision whether you need or want orthogonal grids, which have orthogonality properties, which is maybe nice for the numerics. You want to maybe think about structured versus unstructured grids. You will see examples of cubed sphere is actually a structured grid. Whether you want extra resolution, variable resolution in places, and how your conservation characteristics or geostrophic balance can be represented. And there are a couple of nice review papers about that here by Andy Staniforth and John Thuburn from the UK, or Hilary Weller, also from the UK. Okay, so this is probably a grid that you have seen in the past. So this is no longer it's still in use, let's say, because we do have it in, for example, here at NCAR in the finite volume dynamical core, which is the predecessor for the FE3 dynamical core. Yeah, so this is Laplon. And there are a couple of other models. Endgame was one of them, or is one of them, that are still actually operating on the Laplon grid. Here you kind of see it, and there's convergence here of the meridians at the pole point. There's also a variant of this. This is called the reduced Gaussian grid, and it kind of looks like a Laplon grid, but it's thinned out as we are going here towards the pole point. So you kind of see it here, thinned out, and makes it a little bit more uniform. Yeah? So this is also computationally more efficient because it saves compute. You're just reducing the number of grid points, but you kind of keep the coverage almost constant. This is still used at ECMWF. Right. And another view here of the Laplon grid. This is a nuisance because we need filtering operations to keep things stable. You see the convergence here, the grid spacing becomes super tight. They can be as tight as maybe 10 kilometers or so, and in the polar region, and then 100 kilometers in the equatorial region. But your time step, typical time step, which we hear from Pete tomorrow about it, needs to be stable for the smallest grid spacings. So if you have a grid spacing of 10 in the mesh, you need to be stable for 10. And it's a waste, of course, for the regions that can have 100 kilometer spacing. So the good news about this was, and this has been used forever until the 90s. Yeah, so in the 2000s, we saw the switch over to other grids. Yeah, and you see the other grids here in a minute. This is nice because it's orthogonal. It's nice to implement, easy to implement methods, numerical methods on it. Okay, so the idea was to go actually towards these called platonic solids, and here you see some, to get new grids in place. And these are kind of really neat-looking dodecahedron. You kind of see actually the names. These are structures that fit perfectly into a sphere. Yeah, they do touch the sphere at some corner points. And that's kind of the idea. You see the cube here, which is the base for the cube sphere meshes. And then imagine that you now put a sphere around it, and then you blow it up. You project this cube onto the sphere. And that's your base grid for the cube sphere grid. It has 6 faces, 6 faces of the original cube. But you can do that with many of them. So here's a pentagon. This is called icosahedral grid. These are a little bit fancier and, well, not that much used. They were tried. The upper 3 are operational, actually. These are the base grids for operation models, and the ones here have been used for, exploratory models, but they were not as good. Yeah, let's say it this way. Okay, and here you see them a little bit, once they rotate. This is from a Wikipedia page. You kind of see the structure a little bit there. And this is a structured approach. Of course, this is very coarse. You don't want that grid. Yeah? So now you want to subdivide those faces that you see here with more grid points. But this gives you the structure for your subdivisions. And let's kind of walk through this a little bit. So here's a cubed sphere. Now you see in red, you see the outline of the cube, and in blue you see the subdivisions now on the cube sphere grid, and it's now projected onto the sphere. And this is very popular. So you see a couple of the names here for the models, including the KMSE model or the home screen model at DOE. This is the basis for FE3. Its base, we had tried it in Michigan at some point, and it's also now the basis for ELFRIC, actually, which we hear about from Tom Bendel on Thursday. Well, but I should point out that there are many, many cube spheres. So if I tell you this is a cube sphere grid, or if somebody tells you it's a cube sphere grid, you have no idea what you're talking about, actually, because there are many options, and you need to ask that second question, and we should ask, actually, I think I know the answer, Tom Bendel. Okay, so these are now the versions of the cube sphere grid you could do. This is so-called orthogonal 1, conformal. Almost orthogonal, but it has these, it's almost, has right angles, but it's very bad at corner points. As you see, it has these really small grid spacings, so we don't want that. And then we have the so-called nomic, non-orthogonal mappings. And now we have equidistant, equiangular, equiedge, and they kind of look alike. Yeah? So I don't claim you can really make out the differences, but they are different. And I want to point out this is now a slide I borrowed from Tim, actually. He showed it just a few weeks ago. And also we have a preprint here, if you want to check it out, a preprint up on archive. So these choices for the cube sphere grid, equidistant, equiangular, and equiedge, have very different spacings. Here you see the minimum and maximum area in one face of the cube. And you see that it makes a difference depending now on that, I don't tell you details how this works, but if you can kind of take a look at literature if you want. But you see a big spread, for example, of the spacings. So if I maybe flip back, this is maybe easy to see. These are really smallish, yeah, not super small, but smallish in the equidistant grid. And then here it's really hard to see anything by naked eye. But here we see kind of in blue, here in this grid, the smallest grid spacings, oopsie, are here in the corner points, and then equiangular. This is a choice in EFRIC, I believe, and also in ChemSE. This is the equiangular mesh, and the smallest, here you kind of see a little bit, the smallest grid spacings are in the middle of the edges here of the cube sphere, and then we have the equiedge grid, and that's actually FE3. Yeah, so FE3 has the equidistant, and we have the, in SE, we have the equiangular grid. And here in this grid, the corners actually are the smallest points. And the spread is actually somewhat more, actually. So equiangular is actually the slowest, or the lowest spread, the smallest range. This is medium, and this is a large spread. All right, moving on. Okay, these are cube sphere grids. Now we go to the icosahedral grids. These are triangular grids. So this is now the original icosahedron, and then you can subdivide them. Here you kind of see the steps. Of course, you see them here as planar grids, but you will then project this out onto the sphere. They will become curved. Yeah, you don't want planar grids. And so as you go to higher subdivisions, you get finer grid spacings. And it's interesting to note that this hexagonal grid and this triangular grid, they're actually related. And it's called the dual grid. And you get basically the hexagonal grid if you connect, let's kind of pick a point here. So, if you go in this region and you pick the midpoints of those triangles and you connect them, you get a hexagon. Yeah? And that's how it's done. So these are kind of interchangeably. There are also some special points in this grid. This is true here for the hexagonal grid. You have a mix of pentagons and hexagons. Pentagons are only where, these are basically where only five neighbors meet. Hexagons are where 6 neighbors meet. And that's a consequence of this base grid. There's these special points that touch the sphere. They will be actually different because they only get you pentagons. There are, in this icosahedral grid, there's 12 pentagons. That 5 in each hemisphere, and at the pole, 2 at the poles. Okay, and here is now kind of a blow up. So this is now used at the German Weather Service in our ICON model, or at the Max Planck Institute. We have a research model, Dynamical, here in Paris. That was used at NOAA at the moment, or that's discontinued. And NICAM, this is a Japanese model, has actually a triangular grid. Okay. Coming maybe to NCAR and MPAS, we look at hexagonal grids, actually technically spherical Voronoi grids, but they, for our purpose, they look like hexagonal grids. And here's a depiction of a hexagonal grid. Again, this is just a dual grid of the icosahedral grid. Yeah, the two, you can go back and forth between them. Here you see the original, it's not original, it's, no, that's, is this original? No, this is already subdivided, I believe. Well, this is a really coarse hexagonal grid, I guess. Here we have the, more refined. This is now an MPAS version. This is from MPAS, from the webpage. Here we see some models. There is a research, actually, version of the ICON model from the Germans, which is also on the hexagonal grid. We have MPAS, We have a research model called OLAM, actually, University of Miami, and there was a model, I'm not certain Don is here, at Colorado State University that used that grid, but that's also discontinued. All right, and there's a really special grid, yin-yang grid. I think Adam touched upon that. That's the only model I know uses that is the Canadian model, from Environment Canada. Their operational weather prediction model uses a yin-yang grid. And yin-yang grid you kind of see the makeup. There are really two spherical grids. You chop off the pole points. Here you see, you chop off the pole, and then you have two of them, you rotate one, and then you put them back together, and you get that, and it has an overlap region. And it's very orthogonal, not in the overlap region, but because of spherical grids are orthogonal, nice. But this is also called composite grid, and the only thing is you need to make sure this glue, the seam is okay, yeah, because you solve the equations kind of independently, almost on the two pieces, and you need to glue it together. It needs to be mass conserving. It needs, there is some complexity behind that grid, yeah. But they made it work. It's the operational model at Environment Canada. Right, and then there's these fancy research, and this is not used by anybody, yeah? But you could also dream up composite grids. For example, this is an example, spherical grids with a Cartesian mesh on top here in the polar region to avoid the convergence. Or this is super bad, of course. You see this really great, fine grid spacing here. You don't want to do that, but technically, those can be tried, yeah? Okay, and then last but not least, we also have available these variable resolution meshes on top of the base grid structures. So here you see actually now, this is from the SE model. This is the cube sphere grid with a variable resolution mesh embedded. This is a triangular mesh. This is actually from the German Weather Service, the ICON model. This is FE3. FE3 has the block structure. It's very different when you kind of compare that cube sphere embedded versus here, that from SE. And this is from MPAS. So MPAS has that ability as well with the Voronoi tessellations. This I don't call it hexagonal grid, but the base structure was hexagonal in the first place. This is a very complicated process. In MPAS, it takes weeks to generate these grids. It's not a straightforward thing to do. Okay, but there is, we have good, coverage. We have ChemSE, GFDL, MPAS, OLAM. These are all grids with variable resolution options. And Hilary Weller, she did a study on shallow water models, and she published a couple of those as well here, just as a kind of another view of those grids. Okay. Last but not least, I have one more. Yeah, this is another way of doing variable resolution. That's called stretch grid. And this is often done via this transformation, a coordinate transformation, which is often the one that's often used is, we call this Schmidt transformation. And Schmidt transformation is basically defining a focal point, like for example this here, and then you stretch it towards it. Well, it's actually condensed in that neighborhood. So this is basically, when you think about it, so we have super high resolution here around the focal point, and then it's stretched outward into coarser grid spacings. But it's very homogeneous, meaning, well, homogeneous may be the wrong word. It's very structured. As you see, you are not disrupting. Let me point out, maybe here with the FE3, that this is a very different variable resolution structure where you have very abrupt changes, transitions from fine resolution to coarse resolution. This is also true here. And the more gentle, this is more gentle, yeah. So this is a more gentle zooming approach where you are not doing really abrupt changes. Like this is also actually a concept where you still have defined neighbors. So for example, each cubed sphere grid point has a neighbor to the north, the south, the west, and the east. That's still actually true in this refined mesh. That's not true here because you now have several neighbors actually, depending when you look, here at the interface, there are several neighbors. So this is a more difficult approach actually, if you have those step functions. And as you go to the stretch grid, that's also very smooth, yeah? So it's just a zooming technique basically, but you stretch it really to wide grid spacings on the other side of the globe, yeah? But still, if you're interested, you could do that over, I don't know, United States, you have a weather forecast over the United States and you don't care about the rest of the globe, For short, prediction timescales, that could work. Actually, the Canadians, this is no longer used, but the Canadians had also a Ladulon version before they went to the yin-yang grid. And then they had that stretching, which is actually stretched You kind of see here, it's this is finer here in the pole points, and then they added more resolution here in this neighborhood, and they used that to really have, this is the United States and Canada, they wanted high resolution over the northern, North America for their weather prediction purposes, and that was their technique to get to high resolution. All right, okay, and I close with just a few words on staggering. And this is really an independent decision of all the grid decisions that I just showed you. Basically, you need to ask the question, when you kind of go back maybe to one of those base grids here, where do you put the grid points? Yeah, are you putting them right in the middle? Are you putting them at edges, corners? Well, I should say variables. Yeah, where do you put your unknowns? And that's called staggering. And here's kind of a laundry list to think about. And it's really difficult, yeah? And you will find very opinionated people that will tell you only that grid works, that staggering works, and no other, but other people will tell you differently, yeah? So it's almost a religion, yeah, what people tell you sometimes. Heated debates, I've seen heated debates about that at conferences, but the most obvious choice is to put everything at the same point right in the middle, yeah? That's maybe naive, not naive, but a possible choice. We call that a grid. So that's a possible choice, not naive, because it's actually used in many models. Yeah? Spectral models did that. Actually, the spectral element model, SE model, does that. And there are just some consequences to that decision, yeah? Which you need to deal with diffusion, but you can do that, right? So it's not obvious, actually, how to do it. So here, if you see somebody talk about, and it tells you, I'm using a C grid, I'm using a D grid, I'm using an A grid, it comes actually from a person, Akio Arakawa from UCLA, very senior, very famous, I should say, scientist in atmospheric science. And he invented those naming conventions. And then we have a few, I think the ZM grid was named by Dave Randall, actually. All right. So let's take a look. So here are examples of those staggering options. So a grid would be, and I'm just using a quadrilateral basically, a grid, everything in the middle, yeah, everything. This is, again, this is an example, the SE grid is this temperature and also the velocities, oopsie, right in the middle. The B grid is where you put U and V at edges, well, corners, I should say, and scalars at the midpoint. Also tracers would be in the midpoint. That's called the B grid. The C grid is where you put scalars and tracers in the middle, and you put U at those edges in the direction of the U flow, and V in the direction at edges in the direction of the vertical. It's not the vertical flow, the meridional flow. So this is just an XY cross section. And this is now used in MPAS, but MPAS is on a hexagonal grid. It's not like that in MPAS, but the idea is that. And this is pretty good for divergent motion. Divergent motions are motions, kilometer scale mode, high resolution exposes divergent motions, maybe good for high resolution weather prediction applications. Okay, I should note that this is not a piece of cake, yeah? So if you make a decision, it has consequences in your numerical design later, yeah? So you do need also in the dispersion and diffusion. So you need to worry about it, and we will hear more about that. And we also need, in addition to that, we need a staggering decision in the vertical, which I don't show you, but I keep going here. So we have ABC, now we have D, E, Z, yeah? And the D grid is actually the one used in FE3. What's the difference? It probably looks like the C grid, but not. We exchange the position of U and V. C grid has it switched, yeah? So the D grid here is now switching the positions, but we keep the scalars in the middle. E grid would be where we are putting actually the scalars at corners, and we U and V co-located at edges. And Z grid would be where we are switching away from U and V, and we are going to, these are symbols for vorticity and divergence. And there we would put divergence and vorticity right in the middle. That is actually called the Z grid. I note that this FE3 grid is actually pretty good for rotational motion, but the question is, how good is this for divergent motion? But you could ask the same question about this grid, which is good for divergent motion and maybe less good for rotational motion. And now you pick your battle. What do you want? Where is your interest? Big scales dominated by rotation, small scales dominated by divergence. Yeah. So you need to think about that also as a design decision. All right. And I close with, maybe I have 2 more slides here, with the C-grid. This is now the secret staggering on the hexagonal grid. This is what MPAS uses. So MPAS, looks a little bit different than my C-grid earlier, but here we are basically putting scalars right in the middle, and then we put the u velocities, and this is now vector u velocity, u and v, here at edges, and they are defined normal here to the edge. And then in addition, there's a vertical velocity, which is not shown here. Yeah, so this is actually the secret staggering for the hexagonal grid, and we also can do that for triangulations. So if you are in a icosahedral grid, a secret staggering would look like that, where you put your scalars right in the middle, and u and v you put here at these edges, kind of orthogonal actually to your edge. In addition, I should maybe say this is independent even, independent of the staggering. Let's assume we do A-grid. It's another independent decision. Yeah. Even if you say, okay, let's not worry about staggering. We do A-grid, everything at once, right in the middle. We still can determine where is the middle. Yeah, it's not clear. So you could say, well, right in the middle is this one, or you could also say, no, my A-grid sits at corners. That's an okay decision, yeah? Where we collocate everything at corners, but it does have a huge consequence. If you do an icosahedral grid and you do everything at corners versus you do everything at midpoints, it has actually very different grid spacings. The number of grid cells is not identical. The number of corners is not identical to the number of midpoints in a triangular grid. So you won't need to worry about that. And if somebody tells you this person uses an icosahedral grid and then uses an A-grid, you don't need to ask that question. Oh, where's your position? Is it at corners or is it at midpoints, to understand what the resolution means, actually. All right, let me close here. So what this lecture was about, I just gave you some insight into important design decisions in the dynamical core world. We reviewed the equation sets in today's GCMs. I noted that there are many more equation sets, potentially shallow water, quasi-geostrophic, and so, which I didn't talk about, which you probably use in research mode. We discussed some of the equations, the form of the equations, Lagrangian, Eulerian, flux form, or advective form. We thought about the horizontal grid, saw a couple of choices. We saw some staggering choices, and really what I wanted to set the stage for everything that follows from now on. Yeah? So all the lecturers that go in depth into the numerical schemes will benefit from this generic knowledge. Yeah. Okay, let me stop here and see whether there are questions. Thank you. Yeah.
Question on the mesh grids. Can I assume that inside the mesh, we are solving for things that we are parameterizing outside the mesh, right? Because we have the resolution inside that mesh grid, right?
Mesh grid?
Like
Which mesh?
any mesh where the grid gets higher resolution.
Oh, variable resolution.
Yes.
Yes.
So inside the mesh, we can assume that we can solve for things that we
Yes.
can't outside.
Yes, the physical parameterizations should adapt to that, hopefully. Yeah.
Right. So what do we do at the boundaries? Because at the boundaries between the mesh, right, where we have the physical parameterization, and then inside the mesh we're implicitly solving for it. How do we adjust at those boundary points?
That is a super good research question. Nobody knows that. So, well, we hope that physical parameterizations are built, and that's not actually, it's not guaranteed that physical parameterization will adapt to the mesh size. Physical parameterizations are typically not, they are not built, or they're not built to know about the mesh size. They're just independent. They're column physics. They're just vertical. It's very difficult. Often you see grid imprinting in physical precipitation in those boundary regions. Deep convection is a really big player. Deep convection is rainfall. It's very sensitive to mesh size, and it's often not good. Yeah, you need it's a research problem actually.
Do we trust then the mesh side, like when we're trying to resolve in between the scales?
Well, these variable resolution meshes are typically designed to be. You do it over the United States, for example, for weather prediction purposes. You just run the model for 2 days. You don't worry too much about the garbage that might come in from your edges. Yeah. If you run for long time scales, you do need to worry about it. Let's see.
Are there any adaptive refinements?
Oh, good. Yeah, I took that out. yes, there are not operationally moving meshes. Basically, I myself worked on that actually in the past. Yeah, there are a couple of research options out there for adaptive meshes where a mesh follows a feature like a cyclone, for example, but it's not state of the art in terms of operation. It's a good question. Yeah. Yeah, good question.
So going to the variable meshes, how, if you have different grid sizes for adjoining cells, how are different wave numbers or, the transition of, one grid size can handle up to some wave number, the next one, if it's smaller, can handle a higher wave number. So how's that signal propagation handled across?
Actually, typically, it's taken care of by diffusion. So if, for example, you have a high resolution signal that moves out of your refined mesh into a coarse resolution, where it's it could be aliased, where it can't be represented, but typically diffusion is scale sensitive, so diffusion is acting differently on the meshes, so often takes out the small scales on the higher on the. We have seen with SE actually really good propagation of topical cyclone out of a refined mesh into a coarse domain or vice versa without trouble. Let's see,
How does a grid like the icosahedral grids and MPass, how are those structured when run in parallel? Like the cube sphere, you can run each face kind of distinctly.
It's more subdivided than just each face.
Okay.
It's domain decomposition, so if you just take a look maybe quickly at those here, you just define some chunks, and they don't need to be with they don't need to follow the hexagonal original idea. You just take out chunks. For example, let me just draw a chunk here and a chunk here, and you assign them to different processors, and they do communicate at the edges. It's no problem, actually. Oh, yeah.
Yeah, so I have a question about the different cube spheres. If you have an adaptive mesh on a cube sphere, should that mesh adapt using the same properties as that cube sphere?
It's your choice. We have seen both approaches. We have seen conformal adaptations. Go here. I, again, have worked on this myself. So you can actually, in a cube sphere, you can do that mesh refinement strategy with a propped transition. That's actually probably most people probably use that. Yeah. So you can just embed high-res mesh into a cube sphere mesh and treat that as adaptive mesh refinement. Doesn't need to be that size or that rectangular shape. You can also have multiple meshes. There is one approach now. GFDL is cooperating with NOAA. GFDL. But now the Unified Forecast System, this is a weather prediction system for hurricanes, called HAFS, has actually a cube sphere mesh and has adaptations. Maybe that's the only adaptation that's actually somewhat operational. And there are these blocks of refinement. They do look like blocks like that, and they do follow the hurricanes adaptively. They're not changing shape as they move. They are just blocks. So it's not 100% effective or flexible. But that's a non-conform. That is an approach. I'm not certain I've seen this too much, where you have a smooth transition in your adaptive mesh, but I think that could be important.
So I have two questions on the grid staggering. One, going through like the list of different combinations that you had, was there a combination where we have U and V co-located on the middle of edges?
At the edges, let's see.
Oh, this one, E-grid.
The E-grid, yeah.
So does that one handle both rotation and compressibility better? Because you said one of the advantages of like the D-grid is that it handles rotation pretty well. One of the advantages of, was it the C?
Yeah, this should basically handle both rotation and divergence at the same time. It's also doubling the number of U and Vs you actually have. So actually you have more unknowns in those grids, as you kind of see it here. This has been used at NASA at some point, NASA GIS. They abandoned that now. So it turns out it's not the best choice. Yeah. And your definition of best choice might be different. Yeah, but this had consequences that they didn't like in the end.
Yeah, and my other question was in spectral element methods, we have a whole polynomial basis in each of these elements. Yeah. So how does it work with placing variables at these points if we have a whole set of nodes within our element that represent these variables?
Yeah, you're still in each element, you still have the collocation of all the information. So that's still, I'm not certain, Owen talks about that in a minute here, of the spatial discretization. I think you probably touched upon the spectral element dynamics a little bit. You might touch upon that. But it's still true that everything is co-located, even in those, you're right, there's indeed a basis function approach. It's probably too much for the audience at the moment, but still all co-located. Let me see, I think, well, maybe go here, then come back. Yeah.
Okay, great talk. I have two questions. First is you show the three types of Q-sphere grid, and I want to ask if the equal angular is the best choice, because you show because it seems that they have the same.
Yeah, depends. Yeah, you could argue it's the best because of that. But I think
It's also, it's less regular at the panel edges than the
Oh,
equi
yeah,
edge,
that's
and so that way you potentially have more grid imprinting, which
Yeah.
is another source of error that you.
So that type has the smaller grid type, grid
Yeah.
imprint.
The equi edge does, yes, that's why they chose to change
Yeah,
that.
I didn't list this actually, yes. The best in terms of, and this is kind of this is how big, this factor 1.3 for equiangular grid, how big is your biggest,
It's the ratio of the x to y, like the height to the width.
the x to y dimension,
Yeah.
right? That's 1.4, maybe 1.3, 1.4, and that's bigger here in the equiangular choice than in the equi-edge choice.
It's about 1.05.
Yeah, it's very, very small. So the x and y spacings in this grid are actually almost identical. So if you need that as your characteristic, that actually is a better choice. FE3 has actually an option to go between equiangular and equi-edge. So I don't know whether we could activate that, but
Yeah,
we
that's
could. Actually, there's a
important.
nameless option. FE3 group, if there's a nameless option, if you want to test this, go between equiangular. It's a nameless choice actually between the two sphere grids.
And my second question is that if you choose to use a scratched grid, and the time step is dependent on the small dx.
Yes,
Right.
smallest typically, yeah. I don't think they, at least the ones that use the stretch grid, I'm not aware that they have subcycling techniques in the finite domain. Sometimes if you have that, if you have, this thing, you could imagine you maybe do just a subcycle time step in the small domain, and then you do a longer time step, and then you deal here with the mass conservation and whatever you deal with. Yeah. That's really hard to do in those meshes, which are kind of zoomed, it's less clear what the subcycling should be. Let me, is there another question here? No. Yeah, you had a question.
So, for the variable resolution grids and the stretch grid, which are the advantages of using the stretch grid instead of the variable resolution? Because it seems to me that the variable resolution is a way to use downscaling, but embedded in a GCM, right?
I think the biggest pro of that's super easy to implement. Yeah, it's 2 lines of code basically. Yeah, and doing that, no, very complicated. Yeah, if you and GFTL does even both. They do the stretched version on top of their embedded nests to get super high resolution in a patch. You can even do both. Yeah. This is way simpler.
Yesterday there was a comment on how there had been 10 years of effort on removing mass fixers, and now they're back. So is the need for the mass fixer originally that difference between the advective and flex form?
Yeah.
And then is there a way to understand why they're back, or what's the context?
I'm not certain they're back. It depends what you think or how you want to think about the mass fixer. They're not back for dry mass. Early models were losing dry air mass. That's really bad. But they're still, I don't know whether, when you think about the moist system, there may be even a question, should moist air be conserved? I don't think we have that actually as a characteristic, because we have evaporation, we have rainfall, and that is different at times. So it's maybe even not important. I don't think, I'm not certain actually I can support the statement, maybe you can.
Peter was saying they're back in the ML models.
Yeah.
Oh, in the machine learning models.
Sorry, I
Oh, no,
missed
they're
that.
not back in no, this is the first thing that everybody wanted, mass conservation. All right, yeah, and we do cut in our break, just to let you know, yeah.
How confident are we in the numerical analysis methods for like taking derivatives in a discrete icosahedral mesh or something?
Oh, well, we have some, linear, you can do linear theory. You can get second order. It's very hard to get higher order. MPAS has a little bit of a switch. Again, MPAS group, you might want to look at that. They claim they can do advection, only advection. They don't claim they can do the full dicore at higher order, but they can do advection at fourth order or third order, which is higher. And these orders, we will hear from Owen about that, order of accuracy, what it means. Second order convergence is at least what you want, and icosahedral grids, hexagonal grid typically have that. So it's an okay thing. Spectral element actually way better in terms of order of accuracy. It's kind of more like second, fourth order. But yeah, I guess. Not with the dicore, but not in, well, once you add physics, everything goes down the drain, yeah? Order of accuracy and convergence goes down the drain. All right, another question? Okay. One more, and then we call it.
Can you guys describe a little bit more about this grid imprinting phenomenon? That was, yesterday was the first time I've ever heard of it.
Okay, yeah, that's actually a really good point. Let's maybe go here back to our originals. So grid imprinting is when you see the corners of your original grid in the solution. And that's true for the cube sphere grid. You see 8 corner points, yeah, and these 8 corner points is illustrated here, but these 8 corner points, there are 4 at 45 in the northern mid-latitudes and at minus 45 in the southern mid-latitudes. 4, and that means you might sometimes get a wave number 4 signal in your solution, and that's not because your flow is wave number 4, but your grid created a wave number 4 solution. That's grid imprinting. Yeah. So that's true for, potentially true for FV3 and potentially true for SE, which are built on the cube sphere grid. For MPAS, different. MPAS built here on the hexagonal grid, and that one, dodecahedral, icosahedral grid, hexagonal grid. Yeah, I guess this leads to the hexagonal grid. This is a pentagon. This is the original 12 pentagons. And here we have 12 special points. 2 are at the pole points, and 5 are in the mid-latitudes in the northern hemisphere, and 5 are in the southern mid-latitudes. And that gives grid imprinting of wave number 5, yeah, because of these 5 special points in these mid-latitudes. And then if you see a signal in the MPAS group, it looks like wave number 5, things that repeat itself, that's not flow, that's grid, yeah, that's grid imprinting. So that's what we call it. It's a feature of the numerical scheme and your computational grid. It's always there, you can't get rid of it because there are numerical differences at these corner points that, even insert tiny little things, and every tiny little thing can grow on you, yeah. So it's not something we should be very worried about. At high resolution, it goes away almost, yeah. But you can see it at coarse resolutions. All right, okay, we have now 20-minute break, yeah, and then come back here at 10.
was just like went off the scene and they got it.
That's what we did. I'm so sorry. Didn't want to do it. They were the worst. It's all good.
Testing.
All right, yeah, let's get started. We are a few minutes late. So I was hoping that I, set the stage for the upcoming talks. The next talk is actually Owen Hoots from the University of Michigan. He works in my group, and he will present some ideas about spatial discretization, so horizontal discretization to us, which are on top of course, the grids you choose. All right, the floor is yours.
All right, give me a second. Yeah, okay. Okay, so today I'm going to be talking about horizontal discretization, which if you're not familiar with the jargon, you may not quite know what that is. Firstly, I want to acknowledge that a lot of diagrams in here come from either Christiana's notes or Paul Ulrich's notes. And so if you see a particularly swanky looking diagram, it probably came from Paul. But they expressed exactly what I needed to express, and I didn't want to spend 3 times as much time recreating what was already good. So in this presentation, I'm going to talk about things on a single slide that you can spend weeks or months or years learning really, really deeply. I would love to help you dive in deeper, but everything that I'm going to touch here is going to be a mile wide and an inch deep. I would love to talk more about it and to point you to resources that help you with self-learning in the future. So firstly, I want to start with sort of a framing question. Why do modeling centers maintain specialized fluid solvers for geophysical fluids? Why don't they just use something that was developed for, I don't know, car engines or something like that? Our problem is kind of weirdly shaped, really weirdly shaped, deeply, utterly, weirdly shaped, and I love it. So we're talking mostly here about global models. We're covering the whole globe. And in this, almost always, horizontal spacing will almost always be way bigger than the vertical, even at the highest resolutions that we're simulating these days. The lower boundary of the atmosphere is really rough. The upper boundary of our models is basically fake. Ideally, we would simulate to infinity, but that's not practical. And subgrid parameterization, so the physics, are assumed to operate purely vertically in most models. So toward this end, the vertical dimension is special, and it's usually treated separately for practical reasons. So the calculation of horizontal differential operators, quadrature, calculation of fluxes on the sphere requires a bunch of extra work that's not needed in the vertical. Because you're not really working on a curved manifold in the vertical that has the same properties as the sphere. The vertical dimension often has terrain following. It can be height-based or pressure-based, mass-based. There are these things that allow models to run well that just are completely separate, and you would actually like a discretization of the shallow water equations on the sphere to be runnable with these different vertical coordinates. So the citation I'm giving here is if you have a reason to separate out your vertical coordinate in a systematic way so that you can develop your horizontal numerics without worrying about it, that's been done for a long time in this field. So the dynamical course that we're working with are solving sort of nonlinear hyperbolic partial differential equations. I'm going to use conservation laws in 1D to illustrate the different methods that I'm going to be talking about. So here, basically, Q is some conserved quantity, and F is basically a flux, potentially a nonlinear function of that. And this form basically states that along flow lines, Q is conserved. And sort of the simplest example that I can give is linear advection, for example, with a constant speed, wherein basically your initial distribution is in space. If it's, for example, a sinusoid, that sinusoid will basically be blown by the constant wind at a constant speed. So I want to start out by basically talking about approximating a continuous problem from a finite number of samples. So in this talk, I'm going to be specializing to places where we have discrete samples that are stored at grid points on a sphere. If you're working in there are some models that I'm not going to get into today where that the intuition is slightly different, but for the models that we're working with, you can think of essentially letting Q sub j be an evaluation of some function Q of x at a point x sub j. Basically, I've got a grid point and I've got a value at that grid point. So yeah, we've got discrete points. And we have measurements of some function. So for the next couple of slides, it's a straightforward, like, this is the value of my function Q of x at this point. That won't be true for the whole presentation. But delta x here is basically nominal grid spacing. In this, for everything I'm talking about here, it's constant. But for example, the models we're working with, it is basically the distance between grid points on the sphere. So I'm going to start off approximating a continuous problem. So we have these measurements Q sub j. And we want to represent, the idea is basically we construct a representation Q primed of Q based on our measurements. And then we can differentiate that representation that we create. So on the right here, recall that the time derivative stuff, Pete's going to talk about that tomorrow. So for now, just assume that we can integrate perfectly in time, assuming we can calculate sort of derivatives that are involving spatial variables. So we start, and what you see down here is we have our measurements, and then just sort of what if we just linearly interpolate between them. This gives sort of two notions of, right now I'm talking about sort of finite difference stuff. I'm doing that for, because the math is sort of nice. It's good for educational stuff. It's not really used in many practical models, but there are analogs that we're going to see. So on the left here, so if I go to the point qj, and I take this approximation from the left-hand side, I've got sort of a function for my subgrid, the distribution of Q on between the grid points, and I ask, okay, what's the slope that I derive, and then I've got basically a left derivative or one-sided difference, and I can also do that from the right. And both of those are just, you difference the two values, rise over run, and those two give different values. But the question is, okay, well, I'm talking about approximating the sort of intermediate points as well as I could. I have these 2 points. What if I fit a quadratic through it? Just solve for those things. Then that quadratic is differentiable at qj, so you can just calculate the interpolating polynomial. And then if you differentiate it and then evaluate that at my point x sub j, you get what's called a centered finite difference method, where basically I take the rise over between these two adjacent points surrounding the point where I want to calculate the derivative, and then divide by the run. And so what you can find by doing some Taylor expansion, and this is an exercise that I'd be happy to help you through, it's not too difficult, is basically that the partial derivative of my, if Q is C1, continuous first derivative, then the actual value at x sub j is going to be basically the value that I'm calculating from either of those one-sided differences, the left derivative, right derivative, plus this term O of delta x. I'm not being precise about limits here, but like the idea is basically if you have your grid spacing, the quality of your spatial derivatives is going to double. basically you get, for whatever reduction you get that same amount multiplied out. The centered finite difference that I just introduced, where you take the two adjacent points, you can find that basically you have that the true value is the numerical value you calculate, plus this O of delta x squared term, which means that, for example, if I have my grid spacing, you end up with 4 times better derivatives. So basically, you end up with this squared increase in the quality of your derivatives. And so if you want to think about this further, how would you derive a third order method from this sort of approach? I want to transition right now into the methods that are actually used in the models that you're going to be working with. So starting with finite volume methods like FV3 and MPAS. And to do this, we sort of return to the flux form of a continuity equation that we talked about before. Basically, you have some conserved quantity, and then you have the divergence of a flux that's a function of that quantity. And then the right here is potentially a source term. And we are considering this, think about it on a set omega with a boundary partial omega. And just recall the divergence theorem from Calc 3. You have the integral over the interior of this volume that I'm thinking about. Think of this like an element. Like you have a patchwork on the sphere. You're sort of integrating over it, and the integral of this, the divergence of this flux, you can rewrite that as basically the flux itself dotted with the normal of whatever volume you're integrating around. So this allows us to rewrite the above equation into basically this volume average tendency of a quantity Q, and then you add in basically this term transforms into just the flux across the boundary, and then that is balanced by the integral of the sinks over, sources and sinks over the interior of your domain. And so you might ask, why go to this extra thing? Why add this extra work? Why would it make sense to formulate this in terms of an integral? This sort of weak formulation allows you to model non-differentiable or even discontinuous data, and it's great for problems with steep gradients and shocks, and also makes often makes conservation properties sort of more self-evident to do. So the idea here is basically we have the measurements Qj, like before. We have our sort of the interior of our domain omega, and then we've got the boundary, which are these 2 points either side. And so we've talked about that, let's say that those Qj, those discrete measurements, are a cell averaged value. So what if we just assume that basically the subgrid representation is just constant over the entire interior of the element? Well, we've got discontinuities at the boundary, but basically you end up with an implied flux there, and physically you can derive what you want to do with that. But you don't have to assume that it's constant, just like before with sort of the finite difference thought. What if we chose a subgrid representation of sort of our function that had more degrees of freedom? So we have a linear fit approximating from the points that are adjacent to our point, and just assume that basically the subgrid looks like that. The slope that we calculate here, we've seen it before, and the subgrid suddenly is linear with these sort of jump discontinuities that are happening, that are implied by basically the way we've reconstructed the values on the interior. So once again, we've sort of seen this slope before, so that's an indication that this might be a second order method, that delta x squared like error decrease that I talked about before. So I'm talking mostly about 1D, but in 2D, if you're trying to reconstruct sort of a subgrid features, then you're going to need to incorporate neighboring elements in both directions. If you're in 3 dimensions, then it's going to need to be in 3 directions. And so if you end up with some kind of like subgrid reconstruction, then you can go from a bunch of cell averaged values, and if you set your stencil wider, then you can represent fine scale features within your grid box that are sort of implied by the gradients across your stencil. So once again, why do this extra work? So the subgrid representation contains this implicit information not represented at the grid scale, and the fluxes and these jumps that are sort of implied are constrained by physical characteristics of the equation set. And so I'm showing this diagram. This is vertical velocity at 850 hectopascal from the SE dicore, which I show as an example of basically what happens if you are basically force discontinuities not to exist. So in this particular case, the physics dynamics coupling causes basically grid point scale jumps in particular fields, and due to the sort of properties of SE that I'll talk about later, you end up getting this sort of ringing that happens because the discontinuity is projected out, basically. And so here we get to a bit of jargon that I can't go very deeply on, but a Riemann solver is basically a way of systematically determining the implied flux based on your governing equation. The reason it's called a Riemann solver is because it's formulated in terms of a Riemann problem where you have these constant functions with a jump discontinuity in between it. And so the physical properties of your system are going to define the proper way to define the waves or characteristics that govern how that discontinuity should behave. This is a really deep topic. I've got a book at the end of this that I'll recommend on this kind of thing, and I can't go that deep in it, but it is, these are an intimate part of making a particular finite volume method work. So yeah, subgrid, you've got this sort of subgrid order determined by how you're reconstructing what it looks, what your quantity looks like over beneath the grid scale. FV methods tend to handle discontinuities and steep gradients in a systematic and physically realistic way. Conservation properties and also transport properties like ensuring that moisture doesn't go negative are easier to achieve in implementation. And you can oftentimes guarantee monotonicity that, for example, guarantees that if there shouldn't be new maxima in a particular measured tracer, for example, like ozone, that the way you're solving the transport will not induce that. The locality of the reconstruction means it's really good on modern parallel computers. And yeah, both MPAS and FE3 both use these ideas with very different strategies for how they construct their fluxes, and also the design decisions they make to ensure different conservation properties, because how you reconstruct the fluxes determines what conservation properties are going to be satisfied. So next, I want to talk about the spectral finite element model, starting with sort of a mathematical justification or mathematical explanation of what's going on. The general idea is that you perform integration or quadrature and differentiation exactly by projecting your function onto a function space that's sort of large enough to span your measurements qj. Here I'm, on the bottom, I'm showing here, I'm going to start calling my measurements qi, and then j here is going to start meaning element, meaning that I have these patches, this patchwork that I'm using to cover the globe. And j means, right now I'm talking 1D, so just covering the line, but basically I have an element j and an element adjacent to it, and they're, in our case, they're gonna overlap basically right at the boundary. And on each of these you end up with what are called basis functions, which were mentioned briefly earlier. But the idea is that you, on your particular element, you choose a finite dimensional space of functions to represent that you're going to use to be the best approximation of whatever complicated function you're putting in. So what are shown here is sort of like sinusoids. This principle is can be sort of used for on like a global domain with Fourier analysis, that kind of thing. In our case, we're going to be using polynomials. And so what we sort of start with is, so here on the bottom, I have one element. Right now, we're just thinking about one element, and we have four particular points. We'll call them xj, so j here is element number, and then the index. And so what's happening here, we have 4 points, and we have 4 basis functions. In this case, they are polynomials. And the properties of these are basically that psi1 is 1 on the first point that we've identified here, and 0 everywhere else. And what we see is that psi2 is 1 on the second point and 0 everywhere else, and so on and so forth. Basically, this is a set of interpolating polynomials, where if I have the measurement of a function at this measurement of a function on these 4 points, then sort of the best reconstruction that I can get of it is just the value of whatever q is at this point x times this function. And that, by taking a weighted sum of these functions, you end up with a subgrid representation. And so the x's that are chosen here aren't random. They are, in our case, for the models that we're talking about, they're the GLL quadrature points, which just means that they are chosen to have particular or a particularly good discrete way of calculating the integral of these functions, and also to have relatively nice interpolation properties. So for the models we'll talk about, we've chosen basically 4 points and 4 functions, but something that's sort of unique about this is that you can crank this as basically as high as you want in theory. You add more points, you end up with more basis functions, and you end up having basically a higher order method. So just to give you an idea of how you generalize this to the sphere, the cool thing about rectangular and cubical elements is basically you can get a nice basis for designing a method like this by just basically taking my basis function in x, y, so this 2D basis function is just my 1D basis function of x, and then another one, potentially a different one of these polynomials of y, and you end up with the same property that basically psi hi, if h index is this way and I index is this way, is basically an indicator function. 1 here, 0 everywhere else. 1 here, 0 everywhere else. And so once you've done that, you can basically represent, you have a representation in your function space of whatever q that you're trying to work with. And that has this nice sort of separability where basically you have that your function of x and t is this coefficient that depends on time multiplied by that basis function. And what it turns out is basically that is the measurement at this particular point times the basis function. And so basically, if I just store all of the function evaluations at these points, I can treat them either as grid point measurements of a value or as coefficients of this function. And because of how the points that we've chosen, if I want to calculate the integral over my element of this function, then essentially you go through this intermediate step where these are the coefficients, and then this is just the integral of my time invariant basis function. And that ends up basically creating a discrete quadrature rule, where essentially the sum of these weights times my function is an exact to machine precision representation of the quadrature within that element. Once you've basically said that the actual representation of my function is this product, or the product of the coefficients times these basis functions. So once you have reconstructed this function in this way, you plug it into the partial differential equation. And what happens here is basically this q sub I depends only on t, and so you end up with this basically, not really a partial derivative, you end up with a separation of time and space. And then you end up with the partial with respect to space of the flux function that I talked about earlier, and times basically this reconstruction of my Q. And so now we're going to do something that either is really familiar to you or will be a little bit confusing. So just sort of recall for a moment that if I have an orthogonal basis, for example, in Euclidean space, and I have another vector, I can determine sort of the components of that vector by taking the dot product. So like, you know, in Rn, I've got the v1 to vn, and then just using the standard basis vectors, if I take the dot product of my vector with that part of an orthogonal basis, then I end up with the ith component. And so this one is basically the vector of all zeros except the ith position where there's a 1. So what we're doing next is basically multiplying through by the jth basis function on both sides, and then integrating over the element. And this is an inner product. The analog of a dot product in function space, and basically a very similar thing to what I was showing earlier. And so what's happening here is this is just a purely formal reorganization. You just have the product of, I've added that side j to both sides of the equation, and then separated out the integrals where it was possible. And the next part is the important part, where you can use integration by parts to basically say, okay, there's nothing much I can do about this one, but what I had before was this derivative with respect to x times that, and I can instead say, okay, that's the flux times this basis function at the boundary of an element. Note, we've been working on one element so far, and here we're starting to think about the interface between them. So you end up with this term, and then you end up differentiating your basis functions with respect to x. And so this is sort of a weak form of your conservation law. And what it basically means is that there are these tendencies that can be computed within an element, this one and this one. And then there's a certain degree to which you need to communicate between elements because there are fluxes that are happening between them, which might sound familiar. So if we sort of imagine that we've got element 1 and element 2 here, then the flux between elements basically means that, okay, if I'm trying to reconstruct some value q on this point, on the interior, there's no overlap, there's no conflict. But at this particular point where there's an overlap, you might have two disparate values. And so the question is, how do you handle that discrepancy? There is one option, which is you basically sort of implicitly choose the flux across boundaries so that whatever I'm reconstructing from this left-hand side and whatever I'm reconstructing from this right-hand side agree. I just average them or something like that. And this is sort of a continuous Galerkin approach. Basically, the result is that the representation of or the functions that you're representing are inherently continuous, not necessarily continuously differentiable, but continuous. And this is sort of the closest analog to CAM-SE, what's going on there. And the ringing that I showed earlier is sort of one of the results of saying that if there's a discontinuity, if there is a grid point that's way larger than everywhere else, you're going to end up getting projecting that out. There's another method that I won't be able to get into very deeply, but where you can use a Riemann solver that I mentioned earlier and treat it sort of similarly to a finite volume method, and then you end up with a discontinuous Galerkin method. Okay. I'm sort of, this is a section that applies to basically both models, even if it doesn't immediately seem like it does. So I'm going to talk about that linear advection equation with discontinuous data. These are finite difference simulations, courtesy of James Kent. But the idea is basically, so the initial, or very soon after the initial time, if you have a constant speed and you have this discontinuity in your initial conditions, then the analytic solution you would expect to see is basically that this step function just moves along at a constant rate. On the right here, you're seeing a first order method that is starting to basically show that that steep gradient or discontinuity is sort of being blurred out a little bit. There are diffusive errors that are dominant there. And then on the bottom, you have a slightly higher order method, which retains a steeper gradient, but ends up with this maxima, the sort of spurious maxima that's appearing. You end up with these oscillations that change the range of your data outside of potentially what seems physically reasonable. For example, if this were water vapor, the oscillations happening down here that cause negative values would be inherently unphysical. At a later time, you end up with this is the analytic reference solution, and the first order solution is blurred out pretty significantly as a result of basically dominant diffusive errors, but the minima and maxima of the data remain basically similar. And then in the higher order scheme, you see that not only has the gradient sort of been blurred out a little bit, but the minima and the spurious minima and maxima, these sort of dispersion errors, are getting larger and becoming likely less physical. So there's sort of an idea that is pretty natural to formulate when you're working in sort of a finite volume or flux form style of thinking, where what if you create a scheme that continuously or sort of smoothly degrades to a low order where gradients are high? Basically, there is a theorem that says that if you want all the properties that you want from a transport scheme, and you can't have high order everywhere. It's sort of not possible. And what I'm showing here is basically one way of formulating a way that you create this sort of function phi. There are a bunch of choices that you can make that makes it so that when there is a large difference in gradients between your 2 points, you basically decrease the order of your method down to the point where it becomes, for example, monotonic or, positive definite. Those conditions are phrased this way. And what I'm showing on the bottom here is essentially one scheme, one way of doing that. And what you see on the right here is basically that it's sort of an intermediate between the two cases. It's not as diffusive as first order, but the minima and maxima are preserved, unlike sort of a higher order dispersive approach. So we talked a little bit of, got one more topic and then we're gonna finish up. So we talked earlier about how SE is on an A grid, FV3 is on a D grid, but has some C grid stuff going on. And then MPAS is sort of a C grid model. And what I want to just give you a really brief, really sort of imprecise feel for is why you would want to stagger your grids. So suppose we have a test equation, and this is a sort of linearized set of equations that can predict small amplitude gravity waves in a shallow basin. So basically, it's linear. It's about as simple as possible. I have, that should be a spatial derivative in the partial h, partial t, but that's life. But yeah, basically it models small amplitude waves in a shallow basin. And suppose for a moment that we use an Arakawa A grid, we have all of our variables basically on the same grid. And we'll go back to finite differences because it's sort of easier and there's less bookkeeping. So if you try and calculate it using a centered finite difference method, you say, I want second order, then you end up with just a scheme like this, and we've left the time derivatives continuous like earlier. You end up going over 2 grid points rather than 1, and what you end up potentially seeing on a grid like this is that because you're sort of coupling every other grid point to each other, that things can become sort of uncoupled, and that you can sort of have 2 states evolving on even and odd grid points. But if we go to an Arakawa C grid, so here basically we say, okay, the analog of our velocity is on interfaces, and our height is located at the center of models, then you end up with a centered finite difference method with just a standard sort of delta x here, and you don't end up with those same sort of spurious numerical modes. So there are a lot of details here. I can't even cover all of the horizontal discretizations that are out there. I ended up focusing primarily on the ones that we were talking about here. And as a result, yeah, finite difference methods are great. I would recommend like Randall Levesque's book to sort of get a feel for how different orders and stuff work. It's great for sort of textbook stuff, but they are rarely particularly competitive in the DICOR world, and so they're not really used in practice. Global spectral methods, you take the entire sphere basically as it's sort of analogous to taking the entire sphere as a singular element, and expanding your function in spherical harmonics and doing sort of an analog of the spectral finite element derivation that we did. And that sort of method is what the IFS uses, and it is sort of prone to ringing on a global scale because you have basically global basis functions. You can end up with pretty massive numerical artifacts due to steep gradients. Some older methods are sort of horizontally semi-Lagrangian, meaning you move your grid with the flow and remap to reference positions at regular intervals. Those are less common these days. But yeah, I would like to take questions now.
People didn't get enough coffee? I have a question.
Yeah.
What kind of solvers are the most competitive in the DICOR world right now as far as like the finite volume methods?
So in terms of Riemann solvers,
yeah.
I would say mostly the ones that I know of. Let's see. So FV3 is. Are they exact? Let's see. What?
Yeah,
Yeah, it's PPM formulation, because I know that there are some approximate Raven solvers. I know that there are a couple of exact ones, but yeah. It's, yes?
Yeah, are certain methods like faster or more efficient than others?
So, yes, but that's a very context-dependent question. Basically, one of the things about sort of the history of like dichord development is one of the reasons that like the spectral semi-Lagrangian methods were popular at one point is that at one point you had sort of like monolithic computers as opposed to sort of the modern MPI style of communication. And the things that are good in the era of monolithic computers is different from the things that are performant in the era of CPU-oriented architecture are different from the things that are performant in GPU-oriented architecture. So, I feel like, I don't know if FE3 has made a GPU push yet. Have they? I think so.
I tried Python, but
so,
Python too.
yeah.
Translator, yeah.
Yeah, I mean, one thing that's, so MPAS has tried to have a GPU implementation. I'm not sure how well maintained that is right now. Home and SE, or that dynamical core system, one of the things that comes over with the non-hydrostatic home dynamical core is a performance portable GPU implementation, which means that per watt or whatever, the most efficient compute you're going to get is on a GPU. And so, if you have a bunch of access to GPU resources right now, I mean, I would be hard-pressed not to recommend Home to you. But for example, if you are really sensitive to horizontal resolution or something like that, or looking for variable resolution and trying to tune for that, then the dichord that might be fastest might be completely different. So in terms of dichord performance in this era where Moore's law is kind of dead, it isn't really, it's oftentimes a matter of how quickly do you adapt, and do you run on multiple architectures, or within your model's strengths, how well can you contain your costs? Yeah.
I think I agree with you for solving dynamics. Semi-Lagrangian methods aren't used too much anymore.
Yeah.
But for solving transport,
yeah, tracer transport,
they can be really
absolutely.
good.
Semi-Lagrangian is the way to go. Yes. Yeah.
Yes, that's important. If I may add.
Yeah.
The main cost of for example, a climate model or chemistry model is tracers, because we have by default 33-ish tracers, full chemistry 250 or something like that. So if you compare that to UVT pressure, that's much more expensive. That's what dominates the cost. That's where semi-Lagrangian comes in really handy, because you can take very long time steps.
Yeah, and if you add back in vertical velocity and have to have a little bit of extra numerical treatment to make that work, if you can offset that by having more efficient tracer transport, I mean, that's what we're seeing in SE, in non-hydrostatic SE right now, right? Where basically we can just run non-hydrostatic, but the cost savings in terms of raw tracer transport is astronomical. Yeah.
Yeah, could you go, it's me, right?
Yeah.
Could you go to the slide where you do the integration by parts?
Sure, yeah. There might be a typo in there. I've tried to get as many of them as I could, but.
I think, did you refer to Kasai as being the weak solution?
No.
Oh, no, what was the weak solution?
Basically that, this is a weak formulation. would be what I would say, or basically this is a direction towards weak formulation, right?
Well, Kasai here is like the
Test
polynomial that you're fitting to the points, right?
I mean, it's a test function, yeah.
But couldn't you, like, if you ensure that like your Kasai is continuously differentiable, like what necessitates it being like a weak solution if it is, like if you choose it to be continuously differentiable?
So or basically what's happening here is that we are, so the thing is that for example, Q of X that we determine or how that shows up in this flux could be, or there's nothing in here that requires it to be smooth. Basically, by doing that, by multiplying by a test function and doing the integration by parts thing, basically we have said we're looking at the action of this solution by how it acts on when you take the inner product with a bunch of orthogonal polynomials. And as a result, people can correct me if I'm speaking too loosely, but no, basically the reason I would put it this way is because it is not required, or that basically we have passed off the differentiation to functions that we know are differentiable. Yeah.
For tracer calculation, is there any specific order of calculating a direction in specific direction? Like we do horizontal direction first and then do vertical direction, or all these directions are treated simultaneously?
That's pretty model dependent. So when we say semi-Lagrangian tracer advection, one of the things that, and tracers is not my area of specialty, so I might say something a little bit off. But the idea is basically if you have sort of floating Lagrangian levels and you are considering, and you're allowing them to move with the flow, then you don't have vertical transport, and your horizontal transport just happens along those floating model levels, wherever those are. And so basically, if you are using an Eulerian reference frame, then you have that extra thing, and they're oftentimes handled differently, slightly differently. But at least in the operational alignment models, the emphasis is on if you cannot have that extra vertical advection in there, why would you want to? So yeah.
So if like we want to like perturb, have some external buoyancy for vertical motion, something like surface flux or something, is that all treated by physics model instead of dynamic core?
Well, okay, so I'm not sure I understand your question. Could you...
So what if we have like external forcing such as diabatic heating from the surface that cause the vertical motion?
Yeah.
And if we do the horizontal direction first, then...
Yeah, so the answer depends on whether you're working in a hydrostatic model or a non-hydrostatic model, where, for example, if you have an atmospheric state, for example, of like that's unconditionally unstable in a hydrostatic model, I am not sure how physical the response is going to be because strange things happen. I don't know. Other people can talk more about that. If you have a non-hydrostatic model and you're simulating, for example, at convection resolving scales, then essentially what happens is you end up with where the vertical motion ends up deforming, for example, in a model with a pressure coordinate, it ends up changing how much pressure is in between different model levels. And if you're working in a Lagrangian frame, it's almost always semi-Lagrangian in the vertical, so you remap after a couple of time steps. So basically, you end up with sort of deformation of your moving levels, where it's not so much that you look at the flux across that surface, instead you see how much that surface moves, and then after a particular number of time steps, you remap to reference levels so things don't get too squirrely. Yeah?
What's the difference between spectral elements and finite elements?
So spectral element is a form of finite element. And it's it's sort of unique to having that, or basically where you use these tensor product bases that allow you to, so in like a finite element model on a tetrahedral mesh, trying to find optimal interpolating points gets pretty nasty when you go to higher and higher polynomial order. The condition number of matrices gets squirrely and yada yada. But with either rectangular or cubical elements, you just end up with this tensor product and it's provably optimal and yada yada. So basically, the spectral finite elements is, Mark, you can correct me because you've watched this evolution a lot longer than I have, but it's
No, I think it's just a very particular type of finite element.
Yeah.
Is there a combination of discretization and staggering that you would like to try that hasn't been tested out?
Let's see, because I just.
Okay, you don't.
Well, occasionally people do finite element in the vertical, and I'm curious about. I've always been curious about that. It's not necessarily a staggering thing because I haven't like developed a staggering myself, but the calculations seem pretty tedious. You sort of find a route through it to get the properties that you want, and then keep massaging things until everything balances out in the end. The horizontal, I don't know. Well, the actual answer is basically there's something called structure preserving methods and stuff that like Chris Eldred is talking about at Sandia and shows up a lot of PDs on the sphere. Those people are C-grid fanatics because they have a principled Bible that says it's objectively correct. But also they have a chance of unifying a bunch of things, and they seem to be systematic about a bunch of really tricky conservation stuff where the discretized equations really resemble the continuum equations, and it's quite beautiful. So that's what I would like to try. Yeah. If you want to hear more about structure preserving methods or whatever, I can point you to other people who know what's going on, because I don't.
But they still have the physics dynamics coupling issues with conservation.
Yeah.
Like that doesn't get around that.
Yeah. I mean, one of the things is working on sort of thermodynamics in that framework and trying to get it as consistent as possible, because there's just the fact that once you couple the physical models, all hope is lost. You can require that every parameterization conserves energy in some sense, but you can't necessarily guarantee that they're going to be compatible with the dynamical core, just by virtue of the fact that they're developed by a bunch of different people and we're not re-architecting the entire physics suite every couple of years. Unless you're SEMA.
Go ahead. In the spectral finite element section, you said that you have to project the function onto a function space big enough for all of your measurements. Could you put that in context of like how things scale as a function of horizontal resolution? Like, is that good scaling or not?
So I mean, the thing is that basically cost scales relative to number of grid points. And so what we've done here, or what you sort of do, is you pick out the order that you want. In our case, it's like 4 points. And then basically the computational expense for a particular mesh for that particular thing is just determined by the amount of calculations you have to do on that number of points. So like the number of points determines the number of degrees of freedom in that function space. It just sort of by construction, subject to that like averaging that I talked about, basically. Yeah. And that projection thing is not necessarily trivial. You have to sort of work to make it natural, but the Taylor and Fournier paper I like quite a bit, and sort of talks about that. Nope, that was not it.
We actually should wrap up in a minute here. We have an online speaker waiting for us.
Right.
Yeah, let's thank Owen again. Okay, we announced Greg. So, well, after hearing, two physical talks, we have an element now in DCMIP, which is just before the lunch break, but it's still over an hour away, yeah? Where we have Greg Hakem online. He's an online speaker. He's a professor at the University of Washington in the Atmospheric Sciences Department, but he has developed a deep interest in machine learning, and we are now transitioning into a machine learning element. And we also have David Hall here and Dima. I saw him walk in from Google, and they will also give us their perspective after Greg's talk. So Greg is basically the author of the test cases in the machine learning group that the machine learning folks investigate this week. And it's a really great honor, Greg, that you had time to present this to us and talk about these tests and your conclusions or your insights that you gain from them.
Thanks, Christiane. Can you hear me okay?
Yes, we can hear you.
Okay, let me do a screen share here. How's that? Can you see that okay?
No, we can't see it yet.
Okay. Still no good?
I don't know. Are you seeing anything on your screen or?
Let me try a different share.
Maybe a different window.
Let's try this one.
That looks better. Oh, say frozen. See, I think he's frozen. If let's see, we give it 1 minute. If we can't fix it, we could swap talks. Yeah, I'm not certain he hears me. Greg, if you could please rejoin the Zoom. See whether he comes back. If he can't come back right now, then we might try switching the schedule and try later. Okay. There he is. Hey, Greg. Hope you hear us. We lost you. Yeah.
Yeah, well, that took me down hard. I had to.
Oh my God.
Sorry about that.
All right, try again.
Whoops. There we go. All right, now I got to share again. I'm a little leery about clicking that one again, but let's try it.
Okay. Whatever you clicked.
Let's just try sharing the PowerPoint.
Yes, I think that works.
Can you see that?
Yeah. Oh no. Oh. Oh God, I think we lost him again, no? Oh my God. Oh no. Okay, we give him 1 more minute, and if that doesn't work, we ask David whether he could present early, and we switch the schedule around. Yeah. Yeah, maybe you should keep it in just the plain mode. Yeah, good point. Yeah. Okay, Greg. Maybe please don't press this button again. Just if you could maybe share the presentation, but not in presenter mode.
Okay, yeah, I was wondering if you could just run it there, but maybe that's not going to work. I've never had this problem before, but it seems like Zoom is having a problem interacting with my computer.
Okay.
Okay, so
We did see it before you pressed presenter mode.
yeah, okay. So this you can see.
Yes, that probably works.
Okay, I'm
Yes.
going to leave it there, get the controls out of the way. Sorry about that.
Don't worry, take it away.
Okay, so I'll do an abbreviated version. So this is based on work I did with a student, Sanjit Masanam. He was a high school student at the time. He's now a physics major at UC Santa Barbara. And I guess the students already know about this. I'm delighted to hear that you're going to use these test cases. So they're on GitHub. If you have run into any problems, let me know. I'll do my best to turn around and correct any bugs in real time. Incidentally, these experiments are really CPU friendly. So for those of you out there that don't have access to GPU, everything I did in this paper was on CPU originally. So it's not that bad if you don't have access to a big compute. So the motivation, I think, comes from the fact that these models, these machine learned models, are providing for weather forecasting skill that's comparable or better than the best in the world. That is the European Center for Medium Range Weather Forecasting Integrating Forecast System. There's a lot of new opportunities. These models are extremely efficient, so we can run large ensembles. They have autograd facilities. And the questions I want to address here are, can we use these models for basic science? And to do so, we'd like to develop confidence that they've encoded physics, even if they were not trained to do so. And can we use them for basic science and also for data assimilation? And the takeaway message here is that a set of physics-based tests would be a really helpful part of the training pipeline for these models. I'm hoping to see this for those that are developing models, which I am not, I'm a user, for evaluating these models and for modeling intercomparisons, which is, I think, what you're up to this week. So in the limited time that I have, I'm going to share with you some experiments that are motivated by physics, in particular, space-time initial value problems. And as I'll say in a few moments, a little bit more about this, signal propagation, I think, is a really effective way to assess whether these machine learned models have learned physics or not. And in the interest of time, I'll just focus on one model. It's Pangu weather. Now, there's a whole bunch of other experiments involving data assimilation that I don't have time to get into. So what's not in our experiments are direct comparisons to solutions from physics models. So this really is an essential test, but quite honestly, I think it's a lot harder to run these experiments in physics models than it is in these machine learned models. Most of the experiments I'm going to show you I set up in a couple of days. And I think it's a bit more of a time investment to set these up in physics models. In part because the boundary conditions are inevitably very different with these machine learned models. We don't have control over that. The orography, the land, ocean mass, things like surface fluxes, they come from the data that the models are trained on, which is a reanalysis data set called ERA5 or a model data set in some cases. And I think this is an important direction in the future, is to get this level of control over these machine learned models, analogous to how we have that control with the physics models. And again, the motivating context here is a physics test suite in order to evaluate these models beyond root mean square error and see how they perform on physical problems. And for the students in the room, you're not going to understand if you come from outside the discipline a lot of what I'm going to talk about here. So here is kind of the essence of it in a nutshell. A Green's function approach is you put a little impulse in space and in time, and you look and see how that signal spreads in space and time. And the reason why that's a useful starting point is that physics limits how fast information can propagate through a fluid, through the atmosphere in this context. As you go to small amplitudes in the linear limit, this is set by the maximum and minimum group velocity. So here's a 1D example showing if we have an impulse at the origin. As we go forward in time, this leading ray defines how fast information gets away from that point. And it usually takes the form of a spreading wave packet in many problems. And then as you go to nonlinear amplitudes, that is larger amplitudes, nonlinearity often lends coherence to the solution and gives rise to things like solitary waves and vortex dipoles. So this is a really efficient method for testing all scales at once and to see if these models have learned this sort of behavior. So the overall structure of the experiments I'm going to show you involves an autoregressive map where we have inputs to a neural network N that produce outputs, and we make two modifications. The first modification for one set of experiments is a forcing function that's external to the model. And in the experiment I'm going to show you, that's a model for tropical heating. The other modification we make is such that the mean state that we apply these perturbations to is steady in the absence of forcing and perturbations. So this dx bar simply means if you put in the average, the time average state that we're going to perturb with these localized impulses, that state is an exact solution, a numerically exact solution of the neural network. And that's really handy because it provides space-time control for the localized input. So if you put something in locally, when you see it evolve in space and in time, it's not an artifact of the mean state that it was added to. So I'm probably going to breeze through at least half of these experiments, given the time I lost at the beginning. And again, if you're from outside the field, I'll give you a sense of what from previous research you should expect to see. Then you'll see the solution from the neural network. And you're just looking for a comparison. For those of you that are within the discipline, I think you'll get a little more out of physically what's happening. So the first one is tropical heating. We're going to have a heat source, and we're going to look and see how the atmosphere responds to that. The second one is to look at the development of a localized disturbance in a storm track, the North Pacific storm track in this case. The third one I think is the hardest experiment. It's something called geostrophic adjustment because the atmosphere on Earth is stably stratified most places most of the time, and the planet's rapidly rotating. There's a relationship between pressure and wind that the atmosphere evolves toward, and this is called geostrophic adjustment. And then finally, I don't think I'll have time to talk about the development of seeds to Atlantic hurricanes, but it's in the paper. Okay, tropical heating. This is a classical experiment. There's a response both locally in the tropics where the heating is applied, and then there's an extratropical response that you'll see in a moment. The heating function is localized within 15 degrees of the equator. It has compact support, so it goes to zero at a finite distance. It's uniform through the troposphere, the weather layer of the atmosphere, and the heating rate is relatively weak because it does resonate with stationary modes in the system. So again, this is a very classical experiment. Here is an old result from Ting and Sarderschmuck showing if you put tropical heating over the Western Pacific warm pool, you get this characteristic behavior, this radiation of waves. As the divergent flow tickles the waveguide, you get these planetary waves radiating along a great circle. And so this is how information gets from the tropics, from something like the Madden-Julian oscillation or from ENSO, and it gets communicated through these teleconnection patterns over long distances. Close to the heating, there's theory and idealized experiments and shallow water models to show the response near the heating with a different boundary condition now on a plane. And the response there is something called a Kelvin wave on the equator, where you get convergent flow into heating, and then you get these off-equator gyres on either side of the heating, which are things called Rossby waves. Okay, so diving now into the results for Pengu weather. So here in the gray lines are the 500 hectopascal heights. So that's the time mean state in the absence of any perturbations. If we just autoregressively cycle on that, nothing happens. It's a steady state solution. The heating area is shown in the dashed red line. And after 5 days in the thin lines, you see the height response. And if we step it forward in time, you can see the emergence of these waves that radiate away from the heating in both hemispheres, qualitatively similar to what I showed you in that earlier research. And if you look down in the lower troposphere at 850 hectopascals, and you look within the heating at the wind field, this was a great surprise to me when I saw this, but basically you get the idealized shallow water solution of this Kelvin wave convergence within the heating, and then you get these gyres at the back edge of the heating. Now, there are some spatial inhomogeneities here because there's real topography, there's land-ocean contrast, it's not shallow water, so it's quite different in the real world from what it is in the idealized case, but yet I think you can see quite clearly that the model has captured the essence of what's happening here. For the baroclinic wave simulations, there's a long history to these things. These are basically the storms that we have in the middle latitudes. There's a classic standard test, the Jablonowski-Williamson test, which I'm sure you're going to hear a lot about this week, the standardized test for comparing dynamical cores. We couldn't do this with the machine learned models because there's a protocol here that we couldn't follow. And in particular, we couldn't satisfy the boundary conditions because we have no control over those. The theory, very quickly again, if you look in the longitude height plane, the key thing you need to notice here is that we get these deep waves. It's a packet with peak amplitude, and the waves preferentially radiate downstream to the east at the tropopause, and they radiate upstream at the surface. All right, so just getting right into it. Let me hit the go button here, and you can see what happens in the mean sea level pressure field and the contours. So we get, from that initial seed, we get the development of a mid-latitude cyclone, another one, and then a third one, a hint of a fourth one. You can see the scale is getting smaller as we go upstream, which is what we expect theoretically. And if you look at the color fill, that shows you the specific humidity anomalies at 850 hectopascal. So basically where, if you looked at a satellite image, you would expect to see cloud in this comma shape. And this is very realistic features. It has these fronts, these little kinks in the isobars here, and this strong gradient, this band of anomalously high relative humidity. These are all features that we expect to see with real systems. Looking aloft, here's the initial seed in the upper troposphere and the geopotential height field. And again, letting this go, you see the development of this wave packet as it spreads downstream. Very realistic. So we're really swinging for the fences here. This is a further idealization where we take the zonal means. This is an average of the wintertime mean state across all longitudes. So this is very, very far from anything that the model had seen in its training data. It's a highly idealized case, and here again is the localized perturbation. And if we let that go, you can see the development of this wave packet, which is really realistic. So we're up in the upper troposphere now. We get these shorter waves that radiate downstream, deeper waves, cyclones developing in the surface here, and then we get this characteristic structure of longer waves at the back of the group. Again, this is what we expect to see. And if you make a direct comparison with nature, here's a large sample composite I did with real Pacific cyclones over 20 years ago, showing the meridional wind composite average, and you get this exponential profile to the wave group, and that's very similar to what we see in the Pengu weather idealized solution. Okay, so I'll do one more, the geostrophic adjustment problem. Again, this is the evolution of the pressure and wind field to something like a balanced state. What I'll be doing here is really geostrophic hydrostatic adjustment. So here's a classical experiment done by Lalong and Sundermeyer, where they put a little density perturbation in, and they're doing the opposite sign to what I'm doing. So they put some high density perturbations in right here. And in the velocity field, you see the first thing that happens is there's an outward directed pressure gradient force that accelerates the flow outward. Under the action of ambient rotation, the flow adjusts to a state of balance on the right. And there's also a density adjustment in the vertical plane. So putting the same thing into Pangu weather, I was not expecting to get much out of this. And to my great surprise, the first thing it does in the first hour or two is putting low pressure right on the equator. It produces exactly what you expect to see. It produces convergent flow into the low pressure, which is the opposite sign of what we just saw. And as you go along in time, you notice a few hours later, the winds start to rotate to the right off the equator in the northern hemisphere, and they rotate to the left in the southern hemisphere, and there's very little rotation on the equator. So Pangu weather has apparently learned on appropriate timescales about the Coriolis effect and the formation of these off-equator gyres. And there's also an artifact that you can see right at the end here, where we go from the 1-hour model solution. There's a 24-hour model in Pangu weather, and they're incompatible with one another. So it's still the only model I'm aware of that has this 1-hour model for global numerical weather prediction. So still pretty handy. I'm going to skip over the hurricanes and go to summary and conclusions to leave time for discussion. So I'm really excited that you are thinking about doing these tests, these standardized tests with the machine learning models. I think that is critically important. And so not only the tests that I've previewed for you here, this is just a starting point. There are many other tests that could be added. I think these results are really promising and argue for a closer comparison with solutions from physics models. And if I could put my wish list out there for folks in the room, for the model developers, it would be really great if using these tests as part of your pipeline was something you published along with the root mean squared error. So we want to know not just that you have good forecasts, but what the results of these tests look like. And what I really want is a model hierarchy, ideally one that's configurable rather than having a model that's trained, say, in an aquaplanet context, to have some way of changing some input parameters and specifying to the model that I wish to have a solution without orography, say, or without land-ocean contrast. So that's my optimistic view of the future. Thanks, and I'm happy to take questions. I can't hear you, if that matters.
Yeah, thanks, Greg. Let me see if there are questions in the room, and I might just give the mic to folks.
Hi, thanks for the talk. I was wondering, how many lines of code did it take you to do these experiments?
Well, you can check it yourself on GitHub, but not too many. Tens. I don't think it takes more than 100. The plotting code is probably more extensive. You know, of course, I'm sitting on top of Pangu weather, and I've done this with GraphCast too. But yeah, the code itself for these experiments is really lightweight. I wrote a lot of it in a couple of afternoons.
All right, thanks for the great talk. Here on this slide, you say publish along with root mean square error. What about also other error metrics that sort of take into account, let's say, extreme values more?
Yeah, that's an active area of research in my group, testing these models for extreme events, not just for these idealized cases. And I say that there's reason for optimism, but also we are still missing control over some of these things and how these models might respond to different climates, wildly different than what we have right now. So that's something you can change, for example, CO2 concentrations, or change the rotation rate in a physics model. These are things that we can't quite do as effectively with the machine learned models, but we will, I think, in time.
Thanks, Greg. Have you seen cases where these models fail really badly, idealized cases?
Yeah, the first one that we tried was the NVIDIA model, which I think was the first one where the weights were released publicly. So that was AFNO, I think it was. So they had, before they went to the spherical harmonics neural network, it was only zonal. FFTs, and that one behaved kind of strangely in a way that our initial hypothesis was these models didn't know that the signals could only propagate at finite speed. And we expected on the first inference step to get a global response. And that model was doing something more along those lines. But there's a lot of low-hanging fruit here for students in the room. There is all kinds of stuff that you can do here, starting with this code base and then extending it to other models and other test cases. This is wide open. You could write a paper based upon what you're doing this week at DCMIP. I taught a class last year where we did just that, and 4 papers came out of that class. So it's a great time to be a student working with these tools.
Hi. So this is probably an ignorant question, so I'm sorry for that. But if you're not comparing directly to any physics-based models, how are you quantifying the accuracy of these simulations? Like, how do you know that it's an appropriate response to the perturbations other than just heuristically arguing it looks like what it should?
Yeah, that's a fair criticism, I would say. The first step is, do we get anything that seems qualitatively sensible? So, we've done some quantification of what I just showed you, like the amplitude of those cyclones. Are they consistent with what we expect in nature? I showed you that the structure of the wave packet is at least qualitatively consistent. The geostrophic adjustment, the rotation of the winds is consistent with a Foucault pendulum timescale. So again, it's all qualitatively consistent, which I'd say would argue for more careful comparisons with the physics models. And there, if you want to get quantitative and specific, you're going to have to make a very close comparison between the setups of those 2 different models. And right now, I think that's very difficult to do. But at least these results, I would hope, motivate pursuing those experiments.
Thanks. This is really, really interesting work. My question is about the steady state solution. What do you have to do to find that? That feels like the crux of how all of these experiments work.
Yeah, so the way I did it was I took the wintertime average for the case that I showed you, so December, January, and February from ERA 5, and I used that as the input to Pangu weather. And for one step, it gives basically a tendency, and I literally just subtract that from the output. And so kind of by definition, that gives you the same thing as the input. And so you can test that. You can with that correction, you can put that output back into the input and you just get the same thing back out again. And so that is a way of ensuring, it's an old trick that the modelers know. You do this at the tendency, the model time step with physics models, but apparently it works really well with these machine learned models too, at least the 2 that I've experimented with. Is that clear?
Yeah, I think so. Let me see whether we have more questions in the room. Yes.
Thanks, Greg. Could you mention any of those low-hanging fruit extra dynamics tests for us? Just curiosity.
Yeah, so actually Mike Pritchard and I have a Google Doc. I haven't visited in a while, but we were making a shopping list of tests. They're the standard ones that you'll probably talk about this week. So some of the classics are Held Suarez, in addition to the baroclinic wave test that Christiane developed. There are these other ones. I don't know if the Dynamical core developers still use them, but my favorite, as you can see from my GitHub repository name, are Modon solutions. So these are finite amplitude dipole vortex solutions on the sphere. It is a kind of a classic way of simulating how well the nonlinearity, you collide these things on the sphere. It really is a hard test of the numerics. And I think it'll be a really hard test for these machine learned models. In terms of, so that's kind of high hanging fruit. In terms of the low hanging fruit, I think comparing these machine learned models with one another, even for the tests that are in this paper, would be really, really interesting. I've only done it with GraphCast, and I didn't have a chance to show those solutions here. The solutions are similar, but they're not exactly the same. And why that is, I think, is an interesting question.
Okay, thank you.
You're welcome.
Yeah, that's exactly what we're doing. So we have GraphCast, Circle ForecastNet, and I guess we also have Pangu Weather, which is maybe, Joshua, is this from Greg? Same one, okay. We're also using yours. and have an intercomparison done this week. Yes, so
Sweet.
let you know.
That's awesome.
Okay, let me see if there are more questions. Okay, if not, then thanks a lot, Greg. And if
Thank
you want,
you.
you can stay online. Yeah.
Will do.
Let's
Have a great week,
thank him
everybody.
again. Yeah. So we transition over to David Hall. He's from NVIDIA, and he will, tell us about NVIDIA's plans for machine learning and what they're up to. And stuff.
Hey everybody, nice to see you all again. I'm an old DCMIPper myself. Hi Mark. From about, I don't know how many years ago. Huh? 2016? Yeah, what is that? I don't know, a long time ago. So I just want to introduce myself very briefly for those who don't know me. David Hall. I used to work at NCAR back in 2010. I did dynamical core model development, non-hydrostatic, high-order model method, method modeling environment, whatever HOME stands for, spectral elements, stuff like that. So I did that for about 7 years. Then I joined NVIDIA and transitioned entirely to doing artificial intelligence for pretty much the same kind of thing, weather and climate. And I've been doing that for about 7.5 years. So the short is I'm old. Okay, so is it supposed to do that? I do. And apparently it's transmitting. Oh, okay, let's see, the other pocket works better. Good. Okay. Yeah, I moved it already, so should be okay. We resolved it, I think. All right, so thank you for inviting us to speak with you today. I'm excited to talk about artificial intelligence and its potential for transforming weather and climate research. I'm very excited about the idea of you guys actually testing these things with some of these old dynamical core tests, because that's been something that's been in the back of my head for a very long time, and I've been, meaning to do that and haven't gotten around to it. So I'm grateful that somebody has, or will, or soon has. So Earth-2 is NVIDIA's initiative to advance weather and climate prediction through the integration of artificial intelligence and high-performance computing. It was introduced by our CEO back in November 2021. It was his own idea that he wanted to sort of leap into this field, although this isn't something that NVIDIA really did. He thought, I can probably tackle this climate change thing and get it done in a year or so. So similar to dynamical twins used in engineering applications, Earth-2 seeks to create computationally efficient representations of Earth's atmospheric and climate systems, which enable rapid exploration of environmental scenarios and enhance our understanding of Earth's system dynamics across multiple temporal and spatial scales. So we want to tackle weather, seasonal to subseasonal, climate, basically the whole thing at all physical scales, like very modest goals. So Earth-2 integrates 3 foundational technologies that he once referred to in Berlin as our 3 miracles to advance Earth system modeling. The first is our GPU-accelerated computing architecture, which we use to efficiently generate high-fidelity training data through traditional numerical simulations like the ones we're mostly discussing here today, except GPU-accelerated. This provides the foundation for AI model development because you need data. We leverage deep learning to create computationally efficient models that match traditional accuracy while delivering orders of magnitude speed up, or at least that's the idea, right? So AI models somehow magically are 1,000 to 10,000 times as fast, and we kind of know why and we kind of don't. And our Omniverse digital twin platform enables interactive 3D visualization for immersive exploration of complex Earth system processes. So we make really awesome, pretty pictures with Omniverse. So we had started out with ForecastNet, that first model that we were just hearing in the last talk, and then we've just branched out in a million directions since then, and the list is growing every day, and it's actually getting hard to keep track of. So I'm just going to step through it mostly in time order and highlight some of the more interesting models we've developed and what they do. So our AI research efforts span a wide range of applications from weather to climate across multiple scales, beginning with medium-range global weather forecasting. We started there because it was easiest. AI forecasting offers some major advantages over traditional numerical weather prediction models. First off, it's fast. AI models can generate forecasts thousands of times faster. You can jump like a 6-hour time step ahead instead of having to take all the little time steps in between. It's energy efficient. They use a fraction of the compute and power. It scales, so with AI, we can generate massive ensembles of 10,000 members or more, improving predictions of rare but extreme weather events. With traditional models, you can afford maybe 50 ensemble members. Short model development times also allow for rapid iteration and continuous improvements, something handwritten numerical weather prediction software can't match, as I know from personal experience. But there are also challenges yet to be overcome, of course. At present, AI models are mostly black box systems, which we don't fully understand how they work. They don't guarantee conservation of fundamental physics like energy and momentum unless it is explicitly enforced to do so. You can do that, but it has drawbacks. Models learn fundamental physical processes to some degree, but they can struggle to capture out-of-distribution phenomena and conditions not represented in their training data. The training data basically shapes the algorithm, and if you don't have the right training data, it may not learn what you want it to learn. So ForecastNet, we have version 1 and now version 2, and we keep iterating on it, was our first E2 research effort and the first model that demonstrated that AI can effectively emulate global weather systems at operational resolutions of about 25 kilometers. Developed through NVIDIA's collaboration with Lawrence Berkeley National Lab, it operates at 25K and was comparable to leading operational forecast center models at the time, like IFS. They were already higher than that, but it wasn't completely out of range. We chose weather prediction as our initial focus to establish a proof of concept with readily verifiable results. So climate's a little harder to verify. The name ForecastNet reflects its use of Fourier neural operators, which enable the model to capture global atmospheric dynamics efficiently at scale. And this was sort of a pet project of the people at Lawrence Berkeley, which is also why we went with that. Neural weather models like ForecastNet enable the generation of massive forecast ensembles with thousands of members, which demonstrate their value when predicting dangerous extreme events like Algeria's 2018 heat wave depicted here. While small ensembles often miss critical events, as you can see in this image, the large ForecastNet ensemble contains multiple members. Here we have, I don't know, I can't remember how many are in this one, 100 or so, that identify the potential for a dangerous temperature spike, demonstrating how massive ensemble forecasting could help prevent the loss of life. So if you just throw like 50 ensemble members out there, almost all of them stay below that dotted blue line, which is sort of the danger zone. And if you get enough ensemble members, you can see that there is some chance, a low probability, but not impossible, to get this really extreme, dangerous 51 degrees Celsius event, which was pretty bad, if you know Celsius. So building on ForecastNet's foundation in global prediction, we recognized the need for detailed local forecasts. So that was sort of our next step from global down to local. And the first way to do that was downscaling. So this led to our research in AI downscaling techniques. We made something called NVIDIA CoreDiff, which demonstrated a novel two-step approach to downscaling weather data for the Taiwan region. We worked with Taiwan because they had data and they wanted to work with us. And also Taiwan's relatively important to NVIDIA. That's where all of our chips come from. The model first uses a UNet to generate an initial prediction, then refines it using a diffusion model trained on the residual errors. So you get the smooth part and then you get the little details. This technique successfully converts 25-kilometer aerified data to detailed 2-kilometer resolution outputs. Our initial implementation in the Taiwan region served as an important proof of concept for this hybrid downscaling technology. We tried to get the name changed to WeatherLens instead of CoreDiff because it was a terrible name, but we didn't get it in time, so it's now CoreDiff forever. Okay, so after we succeeded with the Taiwan thing, and you can go online, there's some videos about it working on YouTube. I guess I should have included that. But then we moved on to trying to broaden this. The key to CoreDiff scalability lies in its spatial locality. This property enabled us to extend the approach from Taiwan to the much larger continental US domain, which predicts NOAA's high-resolution rapid refresh type variables, including precipitation patterns. Since its initial release, CORDIF has been expanded to many macro-scale and microscale regions across the globe by various research groups and companies. Tomorrow.io, for example, has like millions of little CORDIFs that they light up when they need them so they can do little local predictions. So after our success with generative downscaling, we turned our attention to the more complex challenge of dynamical downscaling and regional forecasting. So our next step was NVIDIA Stormcast. Stormcast represents a significant step forward in regional AI weather prediction. Developed by Jaideep Pathak of NVIDIA, he's developed some of our, was the lead developer on a number of our models. It moves beyond simple downscaling to become a full mesoscale prediction system. As shown in the diagram, the model combines large-scale synoptic state data with mesoscale information using a hybrid architecture. So what that means is it takes the global state, which is kind of coarse, and the initial conditions that are high resolution that you measure, and then combines the two to basically create a regional prediction without having to do the typical boundary condition thing. So it implicitly defines its boundary conditions from the global state. So this includes a UNet component for deterministic prediction and a denoising diffusion process to capture small-scale dynamics. So it's a generative model, if that means anything to you. The model was trained on high-resolution rapid refresh data to predict kilometer-scale weather phenomena across the continental United States, and it does a pretty good job. Moving on, if I can get it to go. All right, so here's an example. We compare 5 Stormcast ensemble members with the high-resolution rapid refresh baseline data from July 2024. So the composite reflectivity patterns show how Stormcast successfully captures kilometer-scale convective structures. Each ensemble member generates slightly different but physically plausible patterns, demonstrating its ability to model forecast uncertainty at fine scales. So basically, these look like weather forecasts, and that's a good thing. And you can test how good they are and quantify that. So this graph quantifies Stormcast's predictive skill against HER using radar fractional skill scores. The solid lines show HER performance, while dashed lines show Stormcast's ensemble probability match mean, PMM, at different reflectivity thresholds, 20 to 40 decibels. Stormcast maintains competitive performance with HER across all thresholds for forecasts up to 12 hours ahead, with particularly strong results in the first 6 hours. So it works. All right, so the next thing is, all right, so we've got global, we've got downscaling, we've got local forecasts, but what we're still doing is initializing everything by stealing the initial conditions from GFS or IFS. So we're still dependent upon these traditional models to initialize our models and then go really fast. So that's a fundamental limitation that was kind of in our way and still is actually. While AI has made remarkable progress in weather prediction, data assimilation remains a critical barrier to achieving fully AI-driven forecasting systems. Developing effective AI data assimilation unlocks transformative capabilities when it works, from rapid state updates to seamless integration of diverse data sources. So it frees the whole thing to be machine learned, which makes it incredibly fast if we can get it all perfectly integrated. There's a few systems like that now, like Aardvark. Our regen AI data assimilation model employs a diffusion denoiser trained on HER data as well. As shown in the diagram, the model learns to reconstruct atmospheric states from an increasingly noisy version. Using the elucidated diffusion architecture from Karatz et al., the model gradually removes noise to generate physically consistent multivariate atmospheric states at kilometer scale. So in other words, you take all these states, you make them incredibly noisy, and then you learn how to reverse that process. You basically create a map in high-dimensional spaces. As if I start anywhere in this noisy space, I map back onto my surface of reasonable predictions. So regen can use sparse weather station readings to generate full atmospheric states. It iteratively refines its output to match available observations while maintaining realistic weather patterns in areas without measurements. So when you go through this high-dimensional space, you can pin down certain values here and there and force it to look only along the remaining dimensions, and then you get states that match those measurements. These plots demonstrate regen's ability to work with real weather station data. The triangles show actual station measurements across Oklahoma, while the colored regions show the model's generated state estimation. So those are everything in between is basically filled in. The model successfully inpaints the area between sparse station observations in the triangles while maintaining physically realistic weather patterns across the entire domain. So we're just getting started on AI data assimilation, but other people are further along than we are. While our previous work focused on weather prediction out to 2 weeks, the typical medium range scale, achieving longer forecasts requires modeling the complex interactions between the atmosphere and ocean, because you can't predict the weather without predicting the ocean after a certain time. It's pretty important. This brings us to our research on coupled AI systems that target subseasonal to seasonal prediction and moving on to climate scales. ACE, the AI2 climate emulator, represents a major advance in stable ML-based atmospheric modeling. As shown here, ACE's predictions in orange closely track the reference climate model in blue in total precipitable water over a decade-long period. So ACE achieves this stability through spherical Fourier neural operators, which are basically spherical elements that are learned by the AI, while maintaining physical consistency, including near conservation of column moisture. Another model coming out of Dale Duran's group in the University of Washington is DCMIP, the Deep Learning Earth System model, DCMIP, led by our collaborator Dale Duran at University of Washington, represents another breakthrough in long-term climate simulation. These plots compare tropical cyclone patterns across different models, with DCMIP shown in panel F. The black lines trace the annual cycle of storm frequency, while the colored shading indicates storm intensity distribution. The model achieves this realistic seasonal cyclogenesis while maintaining stability over 1,000-year simulations, using a tiny fraction of the time and compute required by traditional Earth system models. So for us, this was a big step forward because up till now, you could simulate a couple of years, maybe 10 years. This model successfully said we can do 1,000 years, and we're getting, which at least proves that we can get toward climate. Climate's a lot harder than weather, so that's why we're moving in that direction. Another of our models in this category, OLA, which is the Ocean-Linked Atmosphere, combines two spherical Fourier neural operators, one for the atmosphere at 24-hour time steps, and another for ocean dynamics at 48-hour time steps at a 1/4 degree resolution. OLA demonstrates realistic ocean-atmosphere coupling, capturing phenomena like tropical waves and ENSO with appropriate spatial and temporal characteristics. This work shows that neural operators can effectively model the complex interactions needed for large ensemble seasonal forecasting. So there's a competition coming out soon about seasonal to subseasonal that we're entering a model into. I don't really know the status of that model, but it'll be really interesting to see how that works out. People are trying to tackle this with AI these days and making good progress. Another promising direction we are, where I'm at in time, oh, not too bad. We are exploring combines traditional physics-based models with ML components. These hybrid approaches aim to enhance existing climate models by selectively replacing or accelerating computationally expensive processes. So instead of replacing the whole model, you take your traditional climate model and you replace, say, the parameterized physics with a learned version of physics. A major challenge with these hybrid models is maintaining stability when the neural networks interact with the traditional physics. Even small errors in the ML emulated process can cascade through the system's dynamics over time, eventually causing simulations to become unstable or crash. This has been a persistent challenge since the first hybrid models were attempted 7 years ago, right when I got started. So you can train them offline, they look like they work great, you plug them into the dynamic model, and the two don't play well together and they explode. People have solved that in different ways, but it's been a real persistent problem. To tackle this challenge in 2023, we released a large benchmark dataset, CLIMSIM, which provides over 100 million labeled examples of climate model states and their associated physical tendencies drawn from high-resolution simulations. By making this rich dataset openly available, we aim to accelerate research on stable machine learning emulators that can reliably replace expensive physics calculations while maintaining model stability. So we wanted to create a nice dataset so people can try this out without having to start from scratch every time. In 2024, we improved this benchmark, CLIMSIM Online, which democratizes access to hybrid climate modeling research through a cloud-friendly containerized workflow. This update removes the need for specialized supercomputing resources, allowing machine learning researchers worldwide to experiment with hybrid models directly in the cloud. Researchers can now rapidly test their emulators and analyze how errors propagate through the system, accelerating the development of stable hybrid approaches, we hope. The results reveal a striking contrast in model behavior. While traditional MLPs in blue quickly lose stability, and UNets alone in cyan show gradual drift, whose physics-constrained approach in red maintains remarkable stability. Even after a full year of simulation, the constrained model's errors remain as low as natural climate variability, which is the black dashed line, marking a crucial step toward reliable hybrid climate modeling. I don't actually know the details of whose work, so I'd have to look that up again. All right, so finally we come to the one that we're working on right now. We're actually working on a lot of them right now, but this is the one we're really excited about at the moment. It's called Climate in a Bottle, and it's trying to tackle climate-ish. So Climate in a Bottle aims to address one of climate science's most pressing infrastructure challenges, the fact that only major supercomputing centers can store and provide access to the petabytes of high-resolution climate simulation data that modern research requires. And as the resolution of that data grows, it becomes increasingly difficult to work with in an interactive fashion. I mean, there are just literally petabytes to exabytes of data, and how do you interact with that? You can't download it onto your computer. It's insane. So what do you do? Yeah, we tried to tackle that problem. Our solution is to compress the information content of these massive data sets into a compact neural network that can generate realistic kilometer-scale atmospheric states on demand. So with just 200 kilobytes of input, basic information like the day of the year, the time of the day, the current sea surface conditions, Climate in a Bottle can produce a 600 megabyte output of 5-kilometer global resolution state, representing a 3,000-fold compression ratio. So you just input some things and it outputs a plausible climate state for that day and time and sea surface temperature conditions. So you don't have to download the data, you just take this tiny little model and you ask it to spit out a state when you need it. This model democratizes access to high-resolution climate information, enabling researchers anywhere to interactively explore climate scenarios, fix corrupted data sets, and generate what-if scenarios without requiring access to supercomputing infrastructure. So you can actually do a lot of different things with this model, but I don't have time to go into all the applications. It can do, it's basically a diffusion model like the things that generate pictures of dogs and cats and stuff, but it generates climate, and it can fill in missing pieces and all kinds of cool stuff. Essentially, we're transforming climate science from a data storage and retrieval problem into a data generation capability that can run anywhere. Sorry, I'm slightly over time. There's more than one way to generate an atmospheric state. You have the traditional autoregressive models, like the ones that we work with normally, but they, in AI, they suffer from error accumulation. So we decided to go with a diffusion model approach instead, which generates the whole state automatically. There's a lot of other benefits and trade-offs. We drew inspiration from computer vision breakthroughs and high-resolution image generation, where they generate a little image and then super resolve it and super resolve it again to get the full detail. Climate in a Bottle uses a two-stage diffusion approach because generating 12 million pixels globally would require over 2 terabytes of GPU memory, and that's impractical even for NVIDIA. By separating global patterns from fine details, we make the problem tractable while maintaining physical consistency across scales. So we generate a kind of like a fuzzy global version, and then we generate each little patch at a time and with a little bit of overlap in between them and get the high-resolution bits for each. A major advantage of diffusion models is their controllability. Users can guide generation with specific inputs. This opens up possibilities for interactive climate exploration that simply aren't possible with traditional simulation approaches. So we can drop a little green dot on the globe and say, I want a hurricane here, and it'll generate a state that has a hurricane there. If you try and generate unphysical states, it refuses because it's not in its training data. So you can't get 2 hurricanes like right next to each other if they don't belong there. So these results show C-Bottle generating realistic atmospheric states with proper spatial patterns, cloud structures, and temporal distributions at 5-kilometer resolution globally. Notice how the fine scale details emerge naturally from our course-defined generation process. So the first result shows the visible light output. So these are the kinds of states that this model generates. Is it real? Is it not? I don't know. Here's a global temperature field. Looks pretty good. Here's infrared outgoing long wave radiation. And the thing is, we can generate these individually. We don't have to generate them all together. You can say, I just want this field, I just want that field. And you can actually, there's more to it. You can actually input data from different sources and output data that looks like different sources. So it's a foundation model as well. Here's the horizontal component of surface winds, all at 5-kilometer resolution. It's in HealPix grid format, if that means anything to you. Okay, so C-Bottle excels at capturing the full spectrum of climate phenomena, from daily cycles to seasonal patterns to extreme events. 3,000 compression ratio means we can fit petabytes of climate information into a model that runs on a single GPU. It can be used for downscaling data in painting, guided generation, bias correction, and exploring what-if scenarios. One limitation of the model is that it currently generates a single atmospheric state at a time, so you can't generate temporally coherent sequences of states. It just jumps around. It's Like each one of these is like independent. However, we're working on that. We're working on variants of the model that overcome this limitation using video diffusion model training, which is ongoing. In this talk, we've covered a lot of different AI models for weather and climate, and there are more being developed behind the scenes, many more. If you are just getting started exploring the potential of AI for Earth system science, NVIDIA's Earth-2 Studio is a pretty good place to start. A lot of people like it because it's easy to use. With just a pip install and a few lines of code, users can get access to a variety of AI models. The Earth-2 Studio SDK provides everything you need from data handling to model inference while remaining flexible enough for custom research. And thanks for inviting me to talk today. I'm already over time, right?
Yeah, that's okay. That's super interesting. Thanks, David. Yeah, let me see whether we have one or two quick questions, and then I suggest we move over to
I'll stick around at lunch so you guys can ask me.
Yes, and that would be great if you could, and then people could catch you. Emma, start with you. I think there's actually a microphone here.
You showed this extreme weather case, I think it was Nigeria in 2018 or something, and that sort of your ensemble did catch it. And I was wondering, to what extent did it actually catch the extreme event, or on the other hand, could it just be that as you add more ensemble members, that just there's a tiny, like there is a chance that extreme weather is going to happen, and that at some point, if you add more ensemble members, it will just pop up?
Yeah, sure.
Like which of those two is kind of...
They're both correct. So when you just have a few representative samples, so what you have is a probability distribution function of all the possible weather outcomes that could exist. Each ensemble member rolls the dice and picks one path through that space, right? So as you add more and more paths, you're just better and better resolving this PDF. And so the PDF has some underlying function, like some shape, like most of the states are here, and then there's a few there, and then of course it trails off to infinity, maybe close to zero, but never really zero. So basically, with more and more and more ensemble members, 1,000, 10,000, 100,000, you get the full shape of this PDF, and you can quantify exactly what the chance is of getting something insane like that. So at a 51-degree extreme weather event, you can see that all these states in the tail, you integrate that area, this is the chance of getting something that bad or worse. And it's 1% or it's 0.0001% like it normally would be. So you can see when it hits some sort of threshold where like, oh my God, there's 5% chance of like this incredibly deadly event, and then you can warn people. With just 50 members, you'll probably miss it entirely because you just don't sample the PDF very well. Make sense?
Yeah.
Okay, let's have one more.
Sorry, my answer.
And then we move over to Dima.
Yeah, how much do you think the diffusion approach has mitigated the smoothing issue in machine learning?
Yeah, so the smoothing issue was sort of obvious from the beginning to some of us, and others of us refused to listen. So when you predict the future and your target that you're training to is something like a single number, the best it can do is the average of the future states. So if this is your current state and it branches out to all these future states, the AI model doesn't know which of those is correct because they're all correct, just within an incredibly small, initial condition perturbation. So what it gives you is the root mean squared error, or the ensemble mean, essentially, of those guys as you integrate into the future. And this is totally predictable and totally expected. So of course it's smoother. The ensemble mean of a bunch of predictions is smoother than any of the predictions and doesn't have the highs and the lows and all that. But people stuck with it for a long time because it's just easier to do it that way. Generative models pick one initial condition and follow it through, just like you do with normal numerical weather prediction, integration, and classification. So you get a single state rather than an average over many states. So generative models like generative adversarial networks and diffusion models are the kinds of models that do this. So after a while, they eventually figured this out, and Stormcast turned into, GenCast turned into, I don't know. The Google model turned into a generative version of it itself when they realized that this was really important for predicting these high frequency details. This is what you need to capture extremes. You don't want a smooth output. So yeah, most models are moving towards generative models like diffusion, and yes, it solves that problem.
Yeah, let's maybe thank David one more time. And And our final speaker before the lunch break is Dima. Oh no, that's the wrong talk actually. It's the number Yes, that's the right one. Thank you. And Dmitry Korkov, and he works for Google. Is that Google? Is that Google Research or Google DeepMind or
Google Research?
Google Research, right? Okay, and he will tell us what Google is.
What about now? Oh yeah, now it's definitely working. All right. Yeah, and so I'm going to talk about some of the projects, not as many, that we have at Google working on weather and climate using AI technologies. I will mostly focus on the neural GCM models, and this is like one of the visualizations from our model because I've been working on this model for, from the very beginning. Okay, so I will start with just briefly saying why this field is really exciting, and it is coming from this AI revolution that is happening in weather forecasting, and I think eventually we'll move to other timescales as well. I'll talk about then some of the model architectures from the models that we've developed at Google, and then talk about some physical consistencies, problems or tests that one could look into for these models. And conclude with some future directions that at least the team that I'm working on sees as exciting opportunities. So what about the AI revolution in weather forecasting? So when the whole thing started 5-6 years ago, people were not sure that these models that are built in a purely data-driven method or fashion would catch up with state-of-the-art, supercomputer-sized physics-based models. But as time went on and the resolutions at which these models were operating and the sizes of the neural networks that were used were increasing, the performance has climbed up quite dramatically. And in the last couple of years, they've surpassed, at least on some of the metrics, or one could say like most of the metrics, but as we all know, there are so many dimensions to making a forecast prediction that it's a little bit hard to define a single metric that you compare on those models on. But generally, in many metrics, they've surpassed what physics-based models produce. And it captured a lot of attention from both top-tier publication journals and government agencies to look into these models and see how they could be used for scientific applications and practical applications as well. So I'll just highlight the models that I'm going to talk about, kind of like what were their spiel or main point that they've achieved. So first, GraphCast showed that they can build a model that has lower root mean squared error compared to ECMWF HRES model, which is a deterministic model at quarter-degree resolution. So a lot of the effort went into scaling these models to produce outputs at high resolution and training them to show that when you look at MSE or root mean squared error across many of the different variables and different levels, you basically get better results on these scorecards. Now, of course, we know that this is maybe a little bit of too much of a machine learning way of looking at things, saying lower is better. If you actually make a forecast that looks like an ensemble mean of plausible futures, it doesn't look like weather. So in that sense, you would say maybe that's not necessarily a better weather forecast. So that's something that we've been dealing or tackling with neural GCM quite a bit. And so the two main points that I would say that we've achieved with the neural GCM work is that we showed that we can achieve both state-of-the-art results in weather forecasting when compared to ensemble predictions. So you could look at things that like continuous rank probability scores, or you could look at RMSE of ensemble means. And then what we showed is that by building these models, kind of like to generate samples of plausible weather states, we can match the performance of ECMWF ensemble. And the other interesting result that we found is that by taking these models that were trained on 3 to 5 day weather forecasts and rolling them out for months, years, and sometimes decades, these models generate realistic climate, sometimes reproducing parts of the climate trend. I should say those were all AMIP studies, so we're forcing those atmospheric models with ocean state. So it's not a climate model yet, it's just how the atmosphere responds to like forcing. But when comparing to atmosphere models within climate models, forced in with the same historic SSTs, neural GCM showed competitive performance. And lastly, to the question that was asked about the smoothing. So yeah, the follow-up to the GraphCast, which originally focused on minimizing RMSE and was trained on mean squared error, which kind of like forces the prediction to look like ensemble mean. Switching, basically using very similar architecture to diffusion-based training, basically alleviates this problem almost completely. And the team has showed that they can basically get better performance than ECMWF ensemble, also at quarter-degree resolution using that type of models. And I'll talk about those architectures in a few moments. So, by a few moments, I mean now. First, I'll just mention, so all of the models that I'm talking about, and I would say most of the models until recently, were trained on ERA5 data. And you'll probably know better than I do how this data is generated, but generally it comes from the combination of having sparse global observations that are integrated with physics-based weather models by the process called variational data assimilation that basically gives you the reanalysis product of our best guess for what the state of the atmosphere was historically. And then these models take this data as ground truth and try to emulate or predict this like forecasting system. And one could imagine building a spectrum of different models. There are the traditional models that are still being improved and developed, and I think there's a lot of value in that. There are more of the ML emulator frameworks where you take different weather states and then you try to learn the transition from one to another. Like, how does the system evolve in a single pass of a neural network? And the type of models that our group has been working on is kind of like the hybrid models that take some parts of the physics that is well understood and maybe other parts replaced with machine learning, and ideally trying to hope to bring the best of the both worlds, but one would see. And some of the advantages, I think, of different approaches is that ML emulators, they use data to learn all of the patterns, and kind of like they're optimized for forecast accuracy because that's literally the loss function that is usually used to train these models. But physics-based models, they kind of like, they're complex but more interpretable, and they're designed to generalize because we're baking in all of those physics priors. So a few notes about the architectures. So GraphCast architecture is basically a big graph neural network that aims to project the weather state from a current time to the one 6 hours later. In a few steps, I mean, there's a lot of details that one could go into, but the whole idea is that the state that is originally represented on the longitude-latitude grid by a message passing is first encoded in a icosahedral graph. There's actually kind of like a nested sequence of meshes that can like connect to one another, and then does several iterations of message passing on this in this latent representation on this graph, and then the state is decoded back onto the longitude-latitude grid. That gives you, at the very beginning, a very poor prediction of what the state of the atmosphere is 6 hours later. But then you can train this model, and it was trained using mean squared error on 1 to 12 steps ahead, which corresponds to up to 3 days rollouts, and then you optimize that. And you can think of like message passing as basically like a very simple algorithm on the graphs, which updates the state of edges and nodes of the graph and kind of like performs some form of like generalized computation on this data structure. The other architecture that I'll mention is neural GCM. So in this work, where we're trying to combine a differentiable dynamical core that we wrote in JAX together with machine learning models to represent physics parameterizations. So this setup is very similar to traditional weather and climate models, except we made the dynamical core differentiable. And all of the physics parameterizations we combine together into a single neural network that operates in a column-based fashion, which takes information about the state of the atmosphere at a specific location and predicts tendencies associated with all of the physical processes not resolved by the dynamical core. And then the state could be integrated in time through many steps, and then regraded or decoded back to pressure levels on which era 5 is defined, and you could kind of like differentiate through this whole process. So maybe to Greg, who was mentioning about a 1-hour step for Pangu. So with neural GCM, you could run models and output things at 5-minute time steps or 30-minute time steps. More frequently, we would do that for 1 hour. But that kind of like has the similar flavor to traditional models, kind of like this composition. The final model that I'll mention in terms of the architecture is GenCast. So GenCast is a conditional denoising diffusion probabilistic model, or DDPM. And instead of just having a single pass that predicts the next state of the weather, it tries to generate or sample a next weather state conditioned on the previous one through a kind of like reverse diffusion process, where you start with basically a sample of the noise, and then you kind of like slowly refine it to the state of the weather at a later time, conditioned on the previous one, and you could repeat this process multiple times. And under the hood, the loss function for the denoising process kind of like approximates log likelihood, which results in the model sampling the states of the weather rather than converging to the ensemble mean, which I will kind of like mention some of the challenges that addresses, which are related to physical consistency. So have not a lot of time left, and I know that you're all hungry, so I'll go fast. So one of the things that people oftentimes look at when studying physical consistency of these models is look at the spectra of the output. And early models had this substantial problem where you look at their prediction at 1 day, it looks sharp, it has a lot of power spectra throughout. You look at the 7-day prediction, and it dips and loses all of the high frequency components. And that is really just a consequence that you're training on MSE. MSE converges to the ensemble mean, therefore it should lose those frequencies. But models that use different loss functions generally tend to preserve those high frequency components, like we did with neural GCM, or with GenCast that uses a denoising process. I should mention that the red there is era 5, and then blue are samples from the GenCast, and then they maintain spectra at later time perfectly fine. So that kind of like solves the blurring problem. And I'll just call out that besides trying to pick a single metric, what we found is that visualizing your forecast is really important. And oftentimes when you look at the comparison of the data that you trained on versus the prediction that you make, you could clearly say like, oh, things did not go quite that well because it doesn't look like weather anymore. And we would play this type of game oftentimes with our models when we would plot multiple realizations of our prediction and one of the era 5 and kind of like play a Turing test. Can we tell which one is the model? And usually sometimes we would, and sometimes we don't. We wouldn't be able to tell it apart, and that's kind of like a good sign. I'll mention that one of the advantages that I'm pretty excited about for hybrid models is that it sometimes allows you to do additional tests of realism. So you could impose things like water budget if you have the separation between dynamics and physics, because then you know what part of the moisture you are advecting and what part is being removed from the system by precipitation and evaporation. So you can diagnose those things directly. And then if you say, I want my model to predict evaporation and precipitation, you can ensure that those together are consistent with your changes in the moisture. And that's something that we studied for these models, and also developed some of the models that predict precipitation patterns by nudging it towards iMerge, which is like an observation-based product. and also visualizations in that work were really helpful, tried to kind of like convince us that, hey, these models that we trained produce more realistic distribution than, let's say, other models or even ERA 5, which is known to underestimate the extreme values. Yeah, in the interest of time, I'm going to skip this part, but this is basically just saying the same thing, that by training on additional data, you could get better representation of the extreme events. And there are some caveats when you can look at the 1-hour intervals of those predictions and how you set up those models, like what do you want to predict, evaporation or precipitation, that could introduce certain artifacts at these intervals, at smaller time intervals. Like, do you get crazy precipitation oscillations throughout or not? Happy to spill more details later on. And finally, the other type of tests that are maybe less direct, but I think still validate models in interesting ways, is by looking at physical consistency at much longer time integration. So they're taking these models that we trained on 3 to 5 days and running these prescribed ocean simulations for months and years and looking at things like biases over long-term integration or generation of realistic tropical cyclones, monsoon wind reversals, and things like that. It all, potentially exposes certain limitations or issues with the model. I think are great tests for physical consistency. And to wrap it up, so we think that AI will revolutionize Earth system modeling, and kind of like eventually we'll see models that rather than tackling different timescales with a different combination of methods, will converge to having a single model that kind of like seamlessly, like integrates from nowcasting to medium range weather to seasonal forecasts and potentially climate nowcasting. And there's still a lot of challenges that we need to address and kind of like different ways to improve these models by including, like high resolution models, more data, reducing biases, building coupled models, and training them for long-term objectives. And at Neural GCM, our current focus is to adding coupled models and kind of like combine the atmospheric model with Neural GCM and coupling it to data-driven ocean and land models, supporting things like additional observation operators and incorporating those to the training pipeline. And we're really trying to lean into an open source side of things, trying to make our code easier to use and enabling new research directions such as downscaling or doing data simulation or building additional couple models. And kind of like in terms of the scientific goals for our team specifically, we're kind of like focusing on S2S timescales and assessing climate variability estimates. So that's it. You're free to run off for the lunch, but this is our small team that or at least the core of our team, and a bunch of people that we interact with as we're building these models, and a couple of open source projects that we've been pushing out, trying to create the ecosystem for doing these experiments. Thank you.
Right. Are there questions for Dima? Oh, you probably don't need the mic, actually. I think we can actually catch your...
I mean, I have so many questions, but I will maybe start with one. It may come out provocative, I don't mean it that. So all these models are trained on observations, and they're trained on the ERA 5, and we all know they have limitations, and the observations won't improve with the same rate as the machine learning has improved over the last years. How do you predict will that affect model development for machine learning in the next years? Because it seems like the machine learning models are coming very close to these.
Yeah, excellent question. I love this. So this, the way I would imagine you is basically asking like, oh, what do you think the extrapolation for this would be? So I absolutely agree that if we had data, going to like hundreds of meters with great resolution, then I would say there would be still a long way that this trend would continue. So my personal guess, and like this is not speaking for the company or anything, is that this, in terms of just like scaling out the resolution with reanalysis data, this is kind of like close to hitting the limit, basically, because a lot of these steps are just like models getting closer and closer to Euro 5. Now, having said that, I think there is a lot of opportunity that these models that can still take advantage of through ML-driven data assimilation, because obtaining better initial conditions by incorporating observations from multiple data sources and like time series of observations, I think is something that is like not fully utilized in the existing models, and that's one avenue that will like continue going forward. And we also have a lot of other observations like satellite images and things like that that are messy and hard to work with, but I think that's definitely the direction that I see everyone's pushing towards, including our group.
Yeah.
So with a lot of these like AI weather forecasting models, there's this point of pride or bragging about outperforming ECMWF forecasts, for example. Can I get these forecasts on my phone? Like, how accessible are the forecasts actually to like everyday people for like, oh, I want to know if it's going to be rainy in Albuquerque on Monday, right?
Mm-hmm.
Like, are these released in that way?
Great question. So yes, to some extent. The ECMWF, fairly early on, actually a lot of people were surprised, they started picking this up and even publishing the forecasts of the models on their website. And they also, they're not, staying behind. They're developing their own models, and they perform also like quite well. And they recently declared one of them to be operational, so they're actually issuing those forecasts that you can access on their website. And there's definitely interest from other teams to kind of like try to productionalize those things. Us as like fairly small team, we're not gunning to try to push our models as fast because so many people, so many things you can do with 3 and a bit.
Okay, maybe one more, Tom, and then we go to lunch.
Thanks. My team in the Met Office has been really excited by Neural GCM because we work on dynamical core development. And one of the debates we've been having is how important in your dynamical core how important is it that the dynamical core itself is good? Because does the kind of the data science part then correct for all of the model errors? And we're kind of interested to know what you think.
Yeah, excellent question. So I'll briefly answer it in a few ways, or like a few bits. So one of them is you would say that it's almost surprising that these models did as well as other models because they have such a small spatial extent. You like look at the basic single column, and then the rest, and like there's a little bit of like extra information coming from the gradients, but the rest is really coming from the advection, like other parts that come from the dynamical core. And so in that sense, and we did the evolution experiment where we turn off the dynamical core completely, and the performance is substantially worse. They're like, oh, actually, it like allows you to catch up to these purely AI-driven models that look at the big chunks. So it's clearly doing something. How critical or important it is, that remains to be seen. There were definitely moments when we still trained models and we got essentially as good of the result as we did in the end, but we had like a bug in the die core with the wrong sign somewhere in like the vertical advection. And we're like, oh. And neural networks were like very nice. They were like, yeah, you know what? I think you messed it up here. I'm going to correct it, and it worked just as fine. So there are definitely challenges with that. And that's also partially why we're trying to look at longer time horizon, because we think that physical priors might play a more important role when you do those integrations for seasonal or multi-year simulations. Partially because you could impose a lot more constraints on this type of system. You could impose conservation or balances locally compared to like a global nudging where you say like, oh, I'm gonna fix the global energy of the system. That's very different from saying I'm fixing the energy that if it like disappears from this cell, it moves elsewhere. Yeah.
Right, then thank you one more time. All All right. Yeah, let's head out for lunch. We then reconvene in the library, you know, after lunch, I don't know, maybe 1:50 or so.